Good evening, my dear JEE Lions. Welcome aboard to the Roar series and ready to roar for the first chapter of 12th standard, which is electrostatics and Gauss law. If you look at H.C. Verma, they have divided this chapter into two parts. The first part being electrostatics field and potential, where you basically talk about point charges and system of charges and even dipoles for that matter, and find out the fields, the energies, the force, and the potentials due to these system of charges or point charges. So that is what we will be dealing in today's lecture. There will be a separate class completely meant for Gauss law, its applications and different geometries like shells, sheets, spheres, conductor properties, and so on and so forth. All right. So this chapter into two parts. This is the first part of it. I hope you are ready to roar, my dear lions. And good evening, Kishori, Divakar, Yashwant, Headshot, Yoga, Akshay. Good evening. Good evening. Good evening. Definitely, definitely. Yep. Okay, let's begin with the class, and I hope you have smashed the like button. In case you haven't done that, mark your attendance quickly, even if you are watching it recorded, because that is your small token of Guru Dakshina towards these lectures, which are absolutely free of cost in English for all the JEE 25 and 26 aspirants. So make sure you do that right away, right now. Yep. And subscribe to the channel so that you do not miss any of my classes on YouTube out here. Good evening. Good evening, PSY. Good evening, Harbani. NEET aspirant also can watch this, but slightly some questions will be of higher level. Hello, Adiksha. Good evening, everyone. Hello, Yashwant. Yes. So let's start with electrostatics. So what is um, this chapter going to deal with? Probably some of you might be very new also to this chapter, or it might have just started in your school or college. See, my dear students, um, you might have definitely played with bits of paper by rubbing on your friend's head, and those pieces of paper get attracted. So there is a magical force between those bits and pieces of paper and the scale which you are rubbed on somebody's head. That magical force is called as the electric force. And that electric force comes because of something called as charges. And these charges are basically of two types. One is positive, one is negative. The positive charge comes because of the protons which are there, in that object. All right, excess protons. And then the negative charge comes because of the electrons which are there in that particular object, in fact, in excess. So these positive and negative elements, play a very important role in creating electrical attraction and repulsion between any two bodies. And that is what this particular topic or unit is going to deal with. If you see the word electrostatics, electro is basically something got to do with that charge, which creates that attraction and repulsion around it, like the bits and pieces of paper. You might have also seen that when you touch a doorknob or shake somebody's hand on a carpet, you get a shock. That shock is again got to do with this particular unit of electrostatics. Static because it is at rest or very low speed. So in this chapter, you will see the charges are almost like at rest or an equilibrium or at very low speeds, and you are going to deal with such systems. The next chapter after Gauss law is actually current electricity, which can also be named as electrodynamics. Electro, charge, dynamics means in motion. So charges under motion, that happens in a wire which carries current. When you have your electrical wires which light up your bulb, fan, AC, TV, etc., the charges are flowing through the wires. So those charges under motion, you study it under current electricity. I hope this distinction is absolutely clear. Yep. Yes, yes, Yashwant, this lecture plus 100 plus problems is good enough for this particular chapter. Just follow the routine which I gave you in yesterday's lecture, the roadmap and the strategy for 99.99 percentile. Just check that out. Okay, it's there in the past session. You can see it in yesterday's part. So this particular electric charge, which creates that notion, of electric force around it. So this electrical charge creates something called as a field, creates a field and can attract, and it can basically attract or it can repel other charges, can attract or repel other charges. Okay, it can attract or repel other charges around it. There are two kinds of charges which are found in nature. One is basically the positive charge. One is basically the positive charge, and it is basically because of the protons present inside any atom. The second type is the negative charge, which is because of the electrons which are present in any atom. You also have a third category which is not positive, not negative. Basically, it is neutral. Basically, it is neutral. It does not have only any charge. So it is a neutral thing, and that is because of, let's say, example, neutrons. It is neither positive nor negative. It will neither attract nor will it repel any other charged particle. Hello, Pranav. Hello, AY Gaming. Yep. So, don't ask such questions. How many questions will come from this chapter? You just have to study. If I tell you 5 questions, what will you do? If I tell you 1 question, what will you do? You'll still study the same chapter in the same, enthusiasm and the same, whatever hard work that you're going to put in. Just because 1 question is being asked, will you study less at this point of time? Obviously, you are not in a batch where you just have to complete the entire syllabus in 1 month. You have good almost like 7 to 8 months. Make sure that you study every chapter in detail. Stop asking such questions. I don't even make such videos where this chapter is only important, this chapter is not important at this point of time. You have to study everything. Please mind it. Okay. So the neutrons N is basically neither going to attract nor is it going to repel anything. So that is what electric charges are. Now you will also see. Just 1 second. Yep. You'll also see like charges will always repel. So like positive will always repel, whereas unlike charges will always attract. So in this particular scenario, you will see there will be some kind of a repulsion. So charges, like charges always end up repelling each other, whereas opposite charges, they will always attract. So opposites attract, and you would have seen this in your school and college also. Two people, whom that this person thinks like this person thinks completely off, and they two are best friends, or they two are very, very good friends. And you wonder how come these two people are very good friends. So, opposites attract. And sometimes you see two people of the very same thinking, or like two toppers, both of them are toppers. Maybe they are not good friends with each other. All right. Or two villains, not good friends with each other. All right. So that is how it works probably even in real life. So opposites attract and like charges will repel. Remember this phrase that a neutral charge charge doesn't exert any force, doesn't experience, or exert any force, doesn't exert or experience any kind of force. That is standard. Next important thing about electrical charges, which is found, is that these charges are always found to be in multiples of something. Like for example, we know that in our economy, right? Probably we have 1 rupee coins. These days we don't get paises. A long time back we used to get paises. So you have a 1 rupee coin, right? Maybe imagine after a few more years that 1 rupee coin is also gone, 5 rupee coin is gone, 2 rupee coin is gone. You only have 10 rupee notes. Imagine you have only 10 rupee notes. So if you want to trade, if you want to buy something, if you want to sell something, you can only keep the cost of your item, or you can only buy an item if it is like in multiples of 10. So for example, it can be 200 rupees, or it can be 150 rupees, or it can be 2100 rupees, or it can be 5 lakh rupees or 500 rupees. These are all fine, or even 30 rupees is fine. But what I cannot have, is 15 rupees or 26 rupees or 2.5 rupees or 100.2 rupees or let's say 5/6 rupees. All these are impossible to achieve using the 10 rupee notes. This is our smallest denomination, also called as the quanta of money. This is also called as the quanta, quanta is a small part, quanta of money which is possible, and every other money that I have is a multiple of this 10 rupees. Hence, I would say the money is quantized. The money is quantized. This is quanta. Everything is multiple of this, so it is quantized. Similarly, you will see in nature, charge is also quantized. You cannot write any random charge. It is not going to really happen only if it is a multiple of a certain value. And what is that certain value? Well, it is 1.6. 1.6 into 10 to the power minus 19, whether you take positive or negative doesn't matter, is the smallest charge possible, is the smallest charge possible, is the smallest charge possible, and every other charge, any charge, any charge, any charge is basically some integral multiples of this particular value, which is 1.6 into 10 to the power minus 19. Actually, that 1.6 into 10 to the power minus 19 is also called as E, basically the charge of an electron. So this is a very, very important thing. Here, basically, n can be any integer. Here n is basically any integer, positive or negative, and the value of E is 1.6 10 to the power minus 19 coulombs. 1.6 10 to the power minus 19 coulombs, which also brings me to the idea, what is the unit of charge? What is the unit? What is the unit of charge? The unit of charge in SI system is basically Coulomb, Symbol for that is C. If I talk about the dimension, if I talk about the dimensions of the charge, well, it is ampere into time. It is ampere raised to 1, time raised to 1. Remember, it is not a fundamental unit. It is a derived unit or derived quantity. It is a derived quantity. It is not a fundamental quantity. Current is a fundamental quantity. Current into time is coulombs. Current into time is basically the coulombs part. Okay, I hope this much is clear. I hope this much is clear. Yeah. Yes, very good. So all these things you should definitely know. Now the next important thing which you should know is that you cannot create a new charge, or nor can you get rid of any charge. You will see, no matter what happens, the total charge in this universe remains conserved. Not just that, if you take an isolated system, isolated means nothing can go out, nothing can come in, just like your classroom when your teacher is inside, and specifically if your teacher is very, very strict. Nobody can exit the classroom for a loo break, nor can you go out for drinking water, nor can you go out to get something, nor can somebody who is late enter the classroom. So that classroom with a strict teacher becomes an isolated classroom. Until the bell rings, nobody can go in or out. So same way, if I have an isolated system, no charge can go out, no charge can come in. Whatever happens within the system stays intact. So you will see the total charge remains conserved in an isolated system. Very, very important. So this is total charge. Total charge remains conserved, in an isolated system. There can be many examples of this. Imagine I have a neutral body. And let's say I break it into two parts. And let's say This one acquires 3 positive charges over it. Naturally, to conserve the total charge, there must be 3 negative charges on this body. It has to happen because the total charge on this was 0. The total final charge must be 0. You can see the charge is conserved. Same way, imagine this. Imagine this. There is one body here, okay, and let's say another, okay, and another body over here. I rub them and then I see what are the final charges on both the bodies. Let's say, for example, this had one positive charge and let's say this had, some 3 or 4 negative charges. Let's say 3 negative charges. I rub them, something happens, some exchange happens, and finally they acquire some charges. If you count the total charge of this system, 1 positive, 3 negative, 3 negatives, 1 positive will make it 2 negative. So the total charge of the system is 2 negative charges, which means, by some reason or some way, just imagine something happens over here, this becomes 2 positive over here, this has, let's say for example, 1 negative over here. Then to conserve the charge, I need to make sure the total charge is 2 negative. Right now there are 2 positives, 1 negative. It is plus 1. So I need to add more 1, 2 and 3 negatives. Just check this out. What has happened over here? What has happened over here? Now the total charge is basically conserved. 1, 2, 3 negatives plus 1 will make it minus 2. 1, 2, 3, 4 negatives plus 2 will still make it negative 2. So this is okay. This is basically okay. There is nothing wrong with this diagram. All right. Everyone understood till this point? Everybody understood it till this point? So you have to basically conserve the total charge of the system. To conserve the total charge of the system. Correct. Very good. So total charge is conserved. So this is the principle of charge conservation. This is the principle of charge conservation. Charge conservation. Keep this in mind. The other one over here, this was the principle of quantization. This was the principle of quantization. Okay, this was the principle of quantization. All these are very, very important things. And I think I have put it down as a summary point also over here. Electric charge is a fundamental, means it's a very elementary property. Anything into existence will have either positive, negative or zero charge. Anything which has mass, all right, you will see that protons, neutrons, all these things, they have mass, they also have charge. Some have no charge, some have positive, some have negative. Positive, positive, negative, negative will repel. Positive with negative, basically unlike, will attract. Okay, and charge is quantized and charge is also conserved. Also, one more thing, just because you move a charge here and there does not mean the charge will change. It will still remain the same. You don't have to know so much about it right now, but just keep in mind that when you move a mass really fast, the mass value changes using relativity principles. But charge is not like that. Just because you move a charge really fast does not mean the charge will change. Okay, mass does change. Okay, when you move a mass really, really fast, closer to the speeds of light, but charge, there is nothing like that. It is relativistically speaking, it is invariant. Okay, so JEE wise, this is not important at all, but just giving you an additional piece of information. So I think let's start with some questions coming up on your screen. How many electrons are there in 16 microcoulomb of charge? 16 microcoulomb of charge. Let's think about it. So we know that the total charge is always n times of E. The total charge is 16 micro. Micro is 10 to the power minus 6. N value I do not know. E value is 1.6 into 10 to the power minus 19, which I can also write it as 16 into 10 to the power minus 20. Right? Now you will see that this particular 16 and this particular 16 will get cancelled. Therefore, this n will be 10 to the power minus 6 is on the top and this 10 to the power minus 20 is below. Therefore, the value of n will become, take 20 on the top, it will become 10 to the power 14. So 10 to the power 14 electrons are there in, in this particular amount of charge. Actually, the charge should have been mentioned as negative, then it is okay, or else, electrons won't be there in positive charge. Yes, 10 to the power 14. Perfect, perfect. Amazing, amazing. Okay, moving on to the next question. If a body is rubbed with another identical body, if a body is rubbed with any other identical body, A and B are the same looking bodies, and it is found that A becomes positively charged as compared to B, then compare the masses of A and B. Who do you think will have higher mass? So you have a body A and you have a body B. A and B are identical, but earlier they were neutral. After you rub them, this becomes, let's say, positively charged. Obviously, an equal amount of negative charge will develop over here. So the question is, who has more mass? Now understand this. When I say a body is neutral, it could mean it has only neutrons, or it has equal number of protons and electrons. Now, usually most of our bodies are made of atoms, so obviously it has protons and electrons in those atoms. So an atom, when I say, is electrically neutral, basically number of protons and number of electrons are equal. But when I say a body is positively charged, that means that some of the electrons have left them. Imagine an atom and the electrons leave. So there will be excess of protons, basically positive charge. If the electrons are acquired by some atom, there will be excess electrons. So that atom will become negative and that body will also become negative. It means that electrons have jumped from here to here, and even electrons have mass. Even electrons have mass. So that's why this mass will be more, whereas these electrons left them. That's why the mass over here will be less, because few of the electrons will leave. So guys, what will be the answer? B's mass will be more than the mass of A. B's mass will be more than the mass of A. Is that clear? Very few people answered it. I can see Adiksha answering it. Very good, Shreya. Yes. Okay. Pay. Very good. Yes. Devakar, answer is not B. It is basically C. B will have more mass, because though tiny mini electrons also have some teeny mini mass, so there will be a marginal mass difference. Do not expect in grams or even milligrams. It will be very, 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 very minute difference. But yes, that is what the question paper setter wants to check, your knowledge and your concept. Okay, so that's why we have to go with the flow. Very good. Very good, Sanjana. You have got admission in Manipal College of Pharmaceutical Sciences. I hope you like the branch, and I hope you do really well in the branch, and really, really study well. Very glad, Sanjana. Happy for you. If you are interested in pharmaceutical sciences and you want to make a career, very good. I am really happy that you finally got a good college and you're excited for it. Very good. If A repels B, B attracts C, C repels D, then multiple options may be correct. Which of the following are correct? This is the next level question, level 2. Let's see if you guys can solve this. Okay. If A repels B, so let's assume, okay, let's take these charges A, B, C, and D. Only one of these options are possible. A is positive or A is basically negative. If A is positive, A repels B. That means this is also positive or this is also negative. B attracts C. That means C is negative or C is positive. If this is negative, this is positive. C repels D. That means C and D are like charges. So it will be something like this. So these are the only two possibilities. This is case 1. This is basically your case 2. These are the only two cases. Now solve and check which of the options are correct. Now solve and check which of the following options are correct, my dear students. Check this out. Come on. First of all, A and C are oppositely charged. A and C are oppositely charged. Definitely correct. B and D are oppositely charged. B and D oppositely charged. Perfectly correct. A and D are oppositely charged. A and D, oppositely charged. Perfect. C and D are like charges. C, D. Yes, like charges. So I think all of them are correct. Yes, complete green. A, B, C, D. All the options are correct. Definitely. Definitely. Okay. All the options are correct. Some of you said only AB or ABD. Some only one. Who was that? Kishori. Very good. Very good, Luffy. Very good, Mesu. Awesome, awesome, awesome. Yes, all of them are actually correct. Okay. So if you take cases and solve it, no, it becomes very easy for you to visualize, or else you'll be only confused just looking at it. So always the trick is to write in the rough work, to solve in the rough work, only then you will get it. If you just mentally visualize, you will lose track of what you were thinking 1 second back. And that is how you make silly mistakes in the exam. Moving to the next part, and that is Coulomb's law. That is the main part of this chapter, and you will see all subsequent things are derived from this. So, my dear students, imagine I tell you, you know, uh, any two charges, positive, negative, whatever, will attract and repel each other. But how much they attract, how much they repel, depends on their distance and also their charges. This sounds very similar to what you might have studied in 11th standard in the chapter of gravitation. Remember, two masses will always attract, and how much is that attraction depends on how far they are and what is their masses. Same way, you will say electrical force also depends in a very similar fashion, and you will see even the formulas are very similar. If you remember gravitation, force of attraction, Newton's law of gravity, which was G m1 m2 by the distance square, you will say electric force is also very similar, some constant into q1 q2 by r square. It's very, very similar. So it feels as if Coulomb copied from Newton and acted very, very cool about it. Yep, both these formulas look very similar, but the major difference between gravity and electrical force is, can somebody tell me what is the major differences? One, let me put gravitational force over here versus Coulomb force or electric force versus electric force. What are the major differences that you can find, my dear students? What are the major differences that you can find? Gravitational force is only attractive. Gravitational force is only attractive, whereas electric force can be attractive, can be repulsive also. Both are possible. Attraction, repulsion, both are possible. Yep. Are all these forces non-contact? Yes. Yes. All these forces are non-contact forces, meaning they do not physically touch. You do not have to touch two masses together. Wireless. All these forces are Wi-Fi. It's not like your wired USB connection. Only then the data transfer will happen. It's like Wi-Fi antennas, and they can communicate with each other wirelessly, and they can attract and repel only and communicate via something called as field. Okay, field is something which you cannot see, which you cannot, you know, put it like a diagram in your charts or your books. It's there, and you can only feel it when you put a mass or put a charge. Another important thing is gravitational force is a very long range force, very long range. Like Earth and Moon, how far they are, still they will attract force. There are tidal effects. All the planets are going around the sun because of the gravitational force of the sun on all the other planets. But you will see the electrons are going in the nucleus inside an atom because of the electric force which is present at a short distance. It's not like I am getting attracted by some other electric charge there and I will have to get pulled by it. No, it's a very short distance force. So it's a very short range force. It is a very short range force. But the interesting thing is, when your distances are very close, then the electric force will dominate too much, and it is much stronger in that range. So in that short range, electric force is a very strong force. It is very strong force in nature. Whereas you will see even gravity, at that particular point of time becomes very, very weak, very, very important. Is that clear? Okay, so these are some basic things which you should know regarding gravitational and electrical forces. Okay, so gravity is also considered as a weak force. It is considered as a very, very weak force. Great, great. Neela, this is one shot marathon. Yep, this is one shot marathon. Okay, okay. Now we'll see the formula. So the value of proportionality constant will differ. Yes, that you can put it for the sake of it. This is G over here. Here you will have K. Okay, you can put that. And it is because of charges. Here it is because of masses. Masses are the cause, of the gravitation. Masses are the cause of the gravitation. Here you can say charges are the cause of charges are the cause of electric force. Charges are the cause of the electric force. That's the main difference between the two. So according to the Coulomb's law, he says that whenever you have two charges, the force between them is inversely proportional to the square of the distance and directly proportional to the product of the charges. That is why it is also called as the inverse square law. Sometimes it is also called as the inverse inverse square inverse square law, because the force between them is proportional to the product of the charges and inversely proportional to the square of the distance between them. That is how it is. Also keep in mind, if one of the charge is big, one of the charge is small, 5 coulomb, 1 coulomb, 10 coulomb, 1.6 coulomb, like that. So tell me, who will exert more force? Will F1 be more or will F2 be more? Imagine this is like 20, 30 coulombs. This is like 1, 2 coulombs, like that. Who will be more? F1 will be more or F2 will be more? Put it up in the chat box. Yep. Kishori, who said that is non-universal? It is universal, Kishori. Yeah, it is universal. It's not universal means a lot of people have this misconception. People think universal means if I'm sitting here, I can apply the force on a very far away planet. That is not what is meaning of universal. Universal means no matter where you go in the universe, the law remains the same. So even if you take the two charges on Mars in other galaxy, still they will apply the same formula. But imagine you drive on the left hand side in India, or in somewhere else you drive on the right hand side. That is not universal. From place to place it changes. So that is the difference between universal versus non-universal. Okay, very good. Yes, both would exert the same force on each other because of Newton's third law. So the force on one because of two and force on two because of one, they both are equal and opposite. So F12 bar is negative of F21 bar. This is Newton's law of motion, the third one. The third Newton's law of motion. Action and reaction. Action and reaction. If a body applies a force on other body, then this body also experiences the same force but in the opposite direction. That's Newton's third law. These two forces act on two different bodies, hence they do not cancel each other. Obviously, imagine this F21 were to act on this one. Yes, they will cancel on that body. But no, it's not like that. This is on this is on this. So they cannot cancel because they are on two different bodies. That is your Newton's third law. Now, if you get rid of this proportionality, what you get is that equality relationship. So let's have a look at it. Let's have a look at it, my dear students. So that force becomes K Q1 Q2 divided by R square, where this K is called as the Coulomb constant. Coulomb constant, which is having a value of 9 into 10 to the power 9 in SI units. You can very easily get the SI units of it. It's not that difficult. Force is in Newton. Check this out. Force is in Newton. So Newton is on the top. Take R square on the top. So it will be meter square. Charge, Coulomb, bring it below. So it will become Coulomb square below. So Newton meter square per Coulomb square will be the SI unit of the Coulomb's constant. Okay, as simple as that. So let's block this off. Let's block this off. But you will see very often instead of using K Q1 Q2 by R square, that K can be also substituted in some other way. Yeah. Sir, Coulomb's law is not applicable in all cases. Why not? It is applicable in which not case? You tell me. Which case you would think it is not applicable? You will also see that this Coulomb's law is often written down like this: 1 by 4 pi epsilon naught Q1 Q2 divided by R square. This is also fine, where that Coulomb's constant, that K is actually 1 divided by 4 pi epsilon naught. 1 divided by 4 pi epsilon naught. That is what you have substituted K as. This epsilon naught, this particular epsilon naught is called as permittivity. It is just a constant, guys. Permittivity of free space or vacuum. Permittivity of free space or vacuum. We'll be talking about it in a bit. For now, just remember 1 by 4 pi epsilon naught is K. It is just a constant. And this number actually comes from Gauss's law. You might be wondering, why is it not 2 pi? Why is it not just 1 by epsilon? Why is it not something else? That thought would have come to your head, right? So the answer for that it is coming from Gauss law, which you'll be studying in the another chapter. Don't worry about it now. Okay, so that is the reason for it. So it is the permittivity of free space, my dear warriors, and it is 8.85 into 10 to the power minus 12. You can get that from here. Substitute K as 9, 10 to the power 9. Move this around and take the inverse. You will see it is approximately this value. Okay, everybody fine till this point? You can guess the unit of permittivity. Can you guess the unit of permittivity? It will be exactly inverse of the Coulomb's constant. It will be exactly inverse of the Coulomb constant. So it will be Coulomb square by Newton square meter square. Sorry, not Newton square, Newton meter square. Newton meter square. It will be exactly inverse because K is on the top, epsilon is below. So if epsilon was on the top, K will come below. That means it will be exactly the reciprocal of these units. Yep, exactly. Yep. Okay. No. Even if the charges are moving, Coulomb's law is valid. It's just that new forces also come into play, which are magnetic in nature. So that is additional force. But the Coulomb's law still remains. The Coulomb's law still remains. The electric force is still there. Apart from the electric force, you also get some magnetic force in motional charges. That is separate. That is additional. Electric force is still there. Okay. So that is completely additional. It is not like your electric force is changing. Electric force is still the same. Yeah, it will probably change with the distance. As the distance increases or decreases, the magnitude might decrease or increase. But additionally, a magnetic force comes, which you will study probably in the next chapter. Yep, it behaves like a current. Okay. Okay. All right. So, Kishori, let me correct you over there. Saying that it is not universal because it is not applicable for spheres or anything, that is wrong. Understand, Coulomb's law is applicable for 2-point charges, fine. But a solid sphere, a ring, a shell, a cube, what is it? It is made up of point charges. So if you add the effects using integration, you still get the net force. So there is another law which will be coming to it, which is called as the superposition in a bit, through which you can find the net force acting on a body, even though Coulomb's law is valid for 2-point charges. Just like gravitation law is valid for 2-point masses, and you integrate, you add up, you sum up the effects and find out the net force. Okay, I hope that is clear. Right? Yep. Okay, so let's continue with the next part, and that is basically the vector form, if I'm not wrong. The vector form will also be there. Yes, the vector form of Coulomb's law, not so useful. Maybe for our board's perspective or just like a very simple objective question, it might come. But other than that, it is not having so much of use. So imagine Q1, Q2 are the two charges and R is the position vector on R is the position vector of this charge. So let me just show it to you properly. R is the position vector of 2 with respect to 1. This is position vector. So position vector is always going to have a start and the end. So this is the position vector of 2 with respect to 1. So R21 is basically R2 bar minus R1 bar. It is the position of 2 with respect to 1. Also R21 hat, let me show that to you. R21 hat unit vector is R21 bar divided by R21's magnitude, which is the distance between them. It is nothing but, simply put, the distance between the two charges. This is your unit position vector. Unit position vector. Unit position vector. So that unit position vector will be something like this. This is R21 hat. Then our force which is there on 2 because of 1. That force on 2 because of 1 will have two parts. One is the magnitude, which is F21, and second is the unit vector. Second is basically that unit vector. Unit vector. Any vector is magnitude times the unit vector. Like any vector can be 5i cap, 7j cap, etc. Or any magnitude times the unit vector in that direction. So what is the magnitude of F21, force between these two charges? It is nothing but K Q1 Q2 divided by R21 whole square. R21 square. But what is the unit vector? That unit vector is R21 hat. That unit vector which we are talking about is actually R21 hat. I hope you can see that. This force and this unit vector are in the same line, same direction. Yep. Everyone with me on this? Thank you, Tejita Reddy. Thank you so much for all the love. So why not substitute the value of R21 hat over here, which we have learned in vectors? So it will be R21 bar divided by R21. R21. Very good. What is R21 into R21 square? That's R21 cube. So this will become K Q1 Q2 divided by R21 cube. But be careful, you also have R21 bar over here. So a lot of people think, sir, it became cubic law, sir. Sir, now cube came, sir. Is it now inverse cube law? No. Because even though there is a cube, there is R21 on the top in vector form. So dimensionally, a meter and a meter will cancel. Meter square is still at the bottom. That's it. So that is just the vector form of your Coulomb's law. As simple as that. Is this point clear till this point? Samuel, you are from Ethiopia and 12th standard. I am preparing for entrance. Then my question to you is the lecture useful for me or not? Please tell me honestly. Samuel, let me tell you, a lot of students from Nigeria, Ethiopia, I think you are probably one of the first ones. But many students from Africa keep watching our classes. And I'll tell you, I have analyzed our channel statistics. Honestly, lot of comments, lot of students and engagement have or has happened from lot of African countries. So if you are preparing for it, please go ahead, because I have personally received some Telegram and Instagram messages, direct messages saying, thank you, sir. It has helped me in the entrance exam. But yeah, I'm not really sure what is your exact syllabus, but I'm guessing it is more or less the same. That's why many students from Africa are watching it. So please go ahead, unless and until there is a big mismatch in the syllabus, which I doubt is going to happen. Is that okay? All right. All right. Shall we continue? Yes. Sir, it should be the magnitude of R21. Yes, Shreya. R21 without the bar is the magnitude. Is the modulus. It's the mod value. It's the magnitude, which is the distance. So that's why I did not put the bar. Yep. Isn't it chapter 1? Yes, it is chapter 1. Yes, it's the same thing. Guys, I hope you know R21 bar's modulus is the same as R21 without the bar. I have told you this in vectors. I've told you this in vectors. You don't put a bar, it's that scalar magnitude. That's all. Okay, you are not putting the bar. So it is the same thing. Don't get confused over here. Cool. Shall we go ahead? Shall we go ahead? Yep. Very good. Very good. Chalo. Let's move ahead. And here is the first level 1 question. Find the vector form of the electric force. Oh, why is it both A and A? This is printing mistake, I believe. So maybe between A and B. All right. So between A and B, find the electric force in vector form. Very simple. Let's try to do this. So vector form, the electric force on B due to A. On B due to A. Both are positive. Both are positive. So if I define a unit vector over here, let's say I call it I cap. If I call it as I cap, then the force on B will be in the same direction. The force on B due to A, because both are going to repel each other. They are going to repel each other. Yes, it is in the same direction. So the vector form of that force will be the magnitude times I cap. Times I cap. I have defined this as the x-axis, this as the y, this as the z. So it's along x-axis. So I cap. I don't even have to worry about it so much now. The force value, my dear students, my dear lions, what will it be? It will be k q1 q2 by r square. It will be k qa qb divided by the distance square, and that I cap just follows. You don't have to do really much about it. Okay, that's why I tell you that this vector form is literally not so useful for us, because it is just telling me one added unit vector. I mean, forget this for a moment. If you look at it, it is just magnitude into unit vector. So the same thing I've done, it's the magnitude into unit vector. K value 9 into 10 to the power 9. Q1 value 2 microcoulomb, so 2 into 10 to the power minus 6. Q2 value 4 into 10 to the power minus 6. Distance 4 centimeters can be written down as 4 into 10 to the power minus 2 meters. So the denominator, hence the denominator will become 4 into 10 to the power minus 2 whole square over here. Let's see what do we get now. 4 square is 16. 4 square is 16. 2 fours are 8. 8. All right. So what are the numbers we are getting? 9 into 8 divided by 4 square is 16. That's what I'm getting. Into all the powers of 10. Let's see. 10 raised to minus 6. 10 raised to minus 6 will make it 10 raised to minus 12. Minus 12 plus 9 will make it 10 to the power minus 3 on the top. This will become 10 to the power minus 4 over here. How can I forget I cap at every stage? At every stage, okay. Continuing the process, this 8 and 16 will cancel 2 times. 9 by 2 is basically 4.5. This will become 10 to the power minus 1 below, which is into 10, which is nothing but 45, which is nothing but 45 I cap. And obviously do not forget the units, which is Newton. So answer is 45 I cap newtons. Is that clear? Mala, I think you missed that too. Yep. All right. Yes. Yes, Shreya. 45 I cap newtons. So this is how you write in vector form. So tell me one thing, my dear students, did you understand this is not so useful unless you are writing board exams? Board examiners fascinate this so much. They get so happy looking at this formula. I don't know for what joy. I mean, it's nothing great. Main thing is this, guys. Main thing is over here or over here. All right. All these are important things. Other than that, it is very straightforward. Moving on to the next question. These kind of questions do repeat in many competitive exams. 2-point charges repel each other with a force of 100 Newton. One of the charge is increased by 10%, other charge decreased by 10%. What's the new force for the same distance? All right, let's do this. What's the new force for the same distance? Come on, my dear students. Are you going to cover both chapter 1 and together in one go? No BTS army, it is going to be separated. Like I said, today point charges mainly. field, force, potential, energy, dipole. This is what we are going to cover. Second part, Gauss law and its applications with geometries and conductors. That is how the division happens. Okay. So you will see H.C. Verma sir has done a very beautiful division on those chapters. I don't like that division in NCERT. It is horrible. I mean, they have mixed capacitors also in it. That's like a complete khichdi. That's like the worst arrangement of chapters that you can possibly think of is there in NCERT. Okay, so that's the reason why we follow H.C. Verma flow. All the coaching institutes follow a peculiar flow which is very different from NCERT. Tejita, you are in 8th standard and you are able to understand everything. Wow, very good. You are going to be one of those students who stick with me till 12th and then tell me, sir, you know, I am there from enthused times. I received few comments few days back. Sir, I know you from We Enthused Days. I'm like, oh my God, how do you know Enthused? That's channel name. When we started, it was called Enthused, then it became Enlight. Now it is just called Vedantu JEE English. So, and they were like, sir, I was studying from you from 8th standard. And now this time when you are discussing the JEE mains paper, you know, I did it very well and now I'm getting a good college. So I'm guessing that will be the same case with you after a couple of years, maybe around 4 or 5 years down the line, right? Congratulations if you are understanding everything. Definitely it's very useful for you. Please go ahead, watch it, right? Okay. So my dear students, what is going to happen over here? 2-point charges repel with 100 Newton, right? Okay. So one charge here, one charge here. I don't care what the values are. I'll just put QQ. How does it matter? Okay. And what happens is the force of repulsion or attraction is 100. 100. Okay. Now what happens the next time you increase the charge by 10%. Guys, tell me one thing. If you increase any quantity by 10%, it will become 1.1 times. Imagine you have 100 rupees. I increase 10%, it will become 110. 110 is 1.1 times of 100. 110 is 1.1 times of 100. So if this is Q, 1.1 times of Q is basically the new charge, So can I say this is 1.1 Q? Same way, think about it. If I reduce the other charge by 10%, how much will that be? If it is 100, it becomes 90. It is 0.9 times 100. So it is 0.9 times the older charge. So should I not say it is 0.9 times of capital Q? There will be a new force between them. Yes or no? So this force will be K Q1, which is 1.1 Q into 0.9 Q divided by R square. Best part, Q and K and R assemble. Just like Avengers assemble, the charges K and R assemble. What you have over here is 1.1 into 0.9. 1.1 into 0.9. Interesting thing to note is KQQ by R square. KQQ by R square is actually 100 Newton. That's the original force. So my dear students, that's nothing but 100. And what you have over here is 11 times 9, which is 99, which is 0.99 because of the decimals. Hence, it will become 99 Newton. 99 Newton is the answer. Very good, Shreya. Very good, Mesu. Excelente. Is there any more session for BitStat? As of now, Sriram, nothing planned because we have a lot of sessions on the channel, older sessions also, you can watch it, okay? That is something which you can use. Very good. Understood, oh, clear, oh, shall we go ahead to the next question, oh? Wow, what a question we have. Two free charges, Q and 4Q, are placed at a distance of D apart. A third charge is placed in between of them at a distance of X from Q such that the system only is in equilibrium. Then what do you think that charge and that distance is the next level question. Let's try to visualize this first, what is exactly happening. Free charges Q and 4Q are placed. Okay, Q. Let me put 4Q. This is Q. This is 4q, and distance is d. Distance is basically d, the distance d apart. So obviously, this q and 4q will repel each other. They will repel each other. Let's say I call it as F1. The force of repulsion between them is F1. Okay, just keep it aside. Now, third charge is placed at a distance of x from small q. Okay, so let's say at a distance of x, you place another charge, which is capital Q. This distance is x. Now think about it. Think about it, my dear students. If the system has to stay in equilibrium, this is only possible if you take any charge and the net force is 0. So for example's sake, let's take this small q charge. The small q is experiencing repulsion because of 4q left side. So to stay in equilibrium, for it to stay at rest, it must experience opposite force by something else. Who is that something else? The capital Q charge. So hence, there must be an attraction between them because of that capital Q. Let's say I call it F2. These two forces should balance each other. Yes or no? These two forces should balance each other. All right, everyone? Everyone? Okay, very good. Awesome. Now, if you notice, all the answers are negative. All the answers are negative because 100% it has to be, because only when they attract will this Q charge remain at equilibrium. So let's equate the two. F1 will be equal to F2. What is the value of F1 between this and this? Between this and this, how much will it be? It will be K Q 4q Q 4q divided by d square is equal to, what is F2? Think about it. The force between these two. It will be nothing but K, then Q, then capital Q divided by what? Just x square. Just x square. So you can see one of the Q, K has got cancelled. And what am I left with over here is just this 4, this number q, this d square is there, and on this side what is left is capital Q and basically x square. But this is only one equation. I have two unknowns. One is the capital Q value, second one is this x value. I want to find that x also. So let's do one more thing over here. Let's do one more thing over here. This and this will also exert some force between them. They will also exert some force between them. So this capital Q on this 4q will apply an attractive force, let's say F3. So for this to stay in equilibrium, these two should be equal. These two should be equal. So guys, can I not say F3 will be equal to F1? F3 will again be equal to basically F1, right? So what is the value of F3? Think about it. F3 will be K 4q into capital Q divided by this distance will be d minus x. This is d, this is x, d minus x. So that's why this will be d minus x whole square is equal to F1, the same F1 which we have used over here. So it will be repulsion between these two charges, which is which is basically K Q into 4Q divided by D square. Now, when you cancel K, when you cancel Q, what you are left with is 4Q divided by D square. And on the left hand side, you are left with 4 capital Q divided by D minus X whole square. You have this equation, what will you do? You have these two equations, what will you do, my dear warriors? I think you can see it right over here. You can equate this with this. You can equate this with this to find the answer. Everybody seeing that? 4q by d square, 4q by d square, equate this with this. Q by x square, 4q by d minus x square. If you want, I will do it on the next page. I'll do it on the next page. So 4q by d minus x whole square will be equal to this one, q by x square will be equal to q by x square. Q will get cancelled. you will take 4 with x square on one side and d minus x whole square on the other side. Taking roots, it will become 2x is equal to d minus x. So therefore 3x, therefore 3x is equal to d, therefore x is equal to d by 3. X is equal to d by 3. Can you see d by 3? In both the options it is there. So B and D options get eliminated. Everyone? Yes. But R for F1 is d minus x ka whole square. Shreya, for F1, what is force F1? It is between Q and 4Q. The distance between Q and 4Q is d. So that is why I have used d. F1 is the force between these two. And the total distance was d. That is why d has been used. Clear? Now, what will you do? What will you do next? What will you do next? Yes, think about it. Yeah, once you have got the value of x, substitute it either here or here, you will get the next answer. Let's say for example here. Let's say for example here only you can substitute and see what is it that you get. So it will just become 4q by d square will become q by x square. X I got it as d by 3. X I got it as d by 3. So d by 3 whole square. D square will cancel. 9 will go on the top. So 9q by, that's it, 9q by d square. If you want, I will write it on the next step. And 4q by d square. D square will cancel. Therefore, from this, what will you get is the value of capital Q. You want the value of capital Q. So capital Q, d square has gone. It will be 4 by 9 times of small q. This is all magnitude wise. This is all magnitude wise. But sign wise, I know q should be negative because it is going to attract. So 4 by 9 is there as option number A, and that is the correct answer. That is the correct answer. Understood how to solve this? Understood how to solve this? Okay. Account, I had made a video on bitsat strategy. Just check out that video or use any bitsat test series video. In that you will find the test series link attached with the coupon code, okay, for 499 rupees. Any video, or if you are not able to find it, leave a comment after this video. Our team will reply to that comment with that particular test series, which you can buy. All right. Next question. 10 microcoulomb charge is divided into two parts and placed 1 centimeter apart so that the repulsive force is maximum. How should the charges be? How should the charges be? Any short method, Kishori? No, this is the method. And the reason why I take long time is because I want to explain everything. But when you do it in your rough sheet, trust me, you will do it within 1.5 minutes. Not more than 1.5 minutes with good practice. Okay, initially it looks long. With practice, 1.5 minutes, max to max 2 minutes. Max to max. Tuck. You would have solved so many problems. Okay, these two charges will attract and repel. Okay, forces are equal. Tuck, tuck, tuck. You will not even write this. You already would have calculated that K and K will cancel and all of that. Immediately, these two charges will also repel and attract. Okay, again, equation for this. Okay, RHS are equal. Okay, let me equate this with this. Tuck, tuck, tuck. You will solve. Two options eliminated. Substitute x over here, tuck, 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 solve it, you will get the answer. It is not that difficult, okay? So with practice, you will find it to be easy. Initial days, it's always like that. Just like when you found vectors very tough, you understood I cap, j cap, k cap probably after quite some time. Just remember that time. How much time you took for understanding kinematic equations or unit vectors and all of that, right? So it always takes some time, okay? Yeah. Motion in 1D next week, Bhuvna. Yep. Okay. So what about this? Whenever you have force between two charges, value is k, q1, q2 by basically r square. I can't touch r, I can't touch k, but I can touch q1 and q2. But there is one thing about q1 and q2. The sum of the charges q1 plus q2 is going to be 10. I want to split the charges somehow so that the force is maximum. Now I'll tell you, just hypothetically take some values like this is 1, this is 9, this is 2, this is 8, this is 3, this is 7, this is 4, this is 6, This is 5, this is 5. After this, it's just a repetition because this will become 6, this will become 4, and so on and so forth. If I just take the multiplication of these two, because I want to make the force maximum, so their product should be maximum, but their sum is constant. 1 into 9, 9, 2 into 8, 16, 7 threes are 21, 6 fours are 24, 5 fives are 25, 24, and so on and so forth. Do you notice one interesting thing? That it is maximum over here. This is the maximum value, and this is exactly what we want to do. We want to make the force maximum. That means the product should be Q1, Q2 should be maximum. Hence, both the charges should be equal. So the answer should be B. Correct. In fact, let me tell you one very interesting property which you can also keep it in your notes. If the sum of two numbers is constant, example, x1 plus x2 is equal to c, then their product, then their product, then their product, basically x1 times of x2 is maximum, when they are equal, is maximum when they are basically equal. Very, very interesting thing. Basically, x1 should be equal to x2, which should be equal to constant by 2. If x1 equals to x2, then both of them should be half and half of their sum. Then their product becomes maximum. You can see that right over here. Is that clear? Yes. Very, very easy. And this has been asked in JEE Mains. Okay. Moving on to the next principle, which is the principle of superposition. And this is the reality of your life also. This is the reality of your life also. So, my dear students, just imagine, there is a Pandu. There is a Pandu, sincere Pandu. What happens is his mom tells, this Pandu, go bring potatoes, from the market. His dad tells, listen Pandu, you go get, something, go get some paint from the shop. Go get some paint from the shop. The teacher tells, go study, get some marks. Go study, get some marks. A friend tells, listen, come with me for the party. Come with me for the party. What will this Pandu do? What will this Pandu do? Well, don't think of yourself and tell me the answer, because I know what you will be like. Sir, very simple. Is this even a question? Why will I go to the market and buy potatoes? Why will I go to the market and buy paint? Why will I go and score marks? My friend is calling me for party. I am obviously going for the party, sir. Okay, that is you. But Pandu, you know what he's going to do? He's going to do everything. Okay. Vedantu, have any faculties from Kerala? Oh, many faculties. You come to the office, so many Mallus are there. Most of our video team is from Kerala. Some of our faculties are also from Kerala. In fact, on my Vedantu NEET English channel, Gopika ma'am is a Mallu. Yes, Gopika ma'am, who teaches awesome biology. She is a Mallu. Okay. So, this Pandu will end up doing everything. This Pandu will end up doing everything. And that's why he's Pandu, guys. He's an all-rounder. So he's listening to everything. Same thing even a charge does. Imagine, like for example, this charge over here, you are placing it near other charges. This charge will repel. This charge will repel. This charge will attract. So what will this charge do? It will experience a net force. It will listen to all these charges, and the vector sum of the forces will apply on this particular charge. So basically, this is called superpositioning. All the instructions given by all these people, mom, dad, teacher, friend, blah, 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 they are being superimposed. They are being superimposed on Pandu, and Pandu ends up doing everything. Same way, this charge also experiences the net force given by the vector addition. This is what you can see over here. This is the principle of superpositioning. As simple as that. Is that clear, everyone? Siva, quite late. We are really Pavam, Divakar. Ooh, why Pavam? Because you are going to go to the party or no? Okay, cool. Let's go. Let's go. Use this superpositioning principle in some of the problems. Wow, directly level 2 question. So I hope you will be able to do it. What say? Okay, ready for the challenge? Let's do this. Okay, directly level 2 guys. Charges q minus 2 and minus q are on the are held fixed at the three corners A, B, C of an equilateral triangle of side A. Find the electric force on the charge at C due to the rest of the two. Interesting. Let's try to solve this. Let's try to solve this by first of all taking up a triangle. Let's draw a beautiful triangle over here. Okay, beautiful triangle. Let's mark the vertices and the charges. Let's mark the charges and the vertices. Vertex A, this is vertex B, this is vertex C. On vertex A, the charge is basically Q. Charge is basically Q. On vertex B, it is basically minus 2Q. And on C, it is basically minus Q. Okay, perfect. Question is find the force on charge C. Okay, this Pavam charge C will experience force because of this as well as this. What is this Q trying to say to this Q? What are they trying to say to each other? Come on, think about it. This Q and this minus Q, they are getting attracted. Why? Because they are opposite in nature. So let's say I call it as F1. No harm, right? What is the value of F1? It will be magnitude wise, K, Q, Q divided by side. Well, the side length is basically A. The side length is basically A. So KQQ divided by A square, which is KQ square divided by A square. That is the force of attraction between the charges kept at A and C because they are opposite in nature. What will B and C say to each other? Both are negative. Both are negative, right? So what will happen? Shaurya Omar? Well, if you're in class 11th, it is not mandatory for you to see it. But yeah, if you are done with your syllabus, most of it, whatever has been taught till now, then yes, please go ahead with it. You will definitely be learning whatever anyways you have to learn after 1 year. So you'll get more time later on. So that's a very good move if you want to do it. So they are going to repel each other again. And the repulsion will be along this line. And that force will be F2, which will be KQQ magnitude wise. K, Q and 2Q. Q, 2Q again divided by A square. So it will be 2KQ square divided by A square. Oh, these two forces, one force is like this, F1. The other force is like this over here. This is F2. Can you guess the angle between these two forces? Come on, my dear students, it's not that difficult because this internal angle is 60 degrees of an equilateral triangle. So naturally, that angle should be 120 degrees. So just mark this angle as 120 degrees. And what I want to do now is find the net force. I want to find the net force. So this is the net force. And what is the net force? Use the vector addition formula. So F net will be root of F1 square plus F2 square plus 2 F1 F2 cos 120. That is what the formula is. All right. But you know what the best part is in F1 and F2? F1 and F2, Q square, A square, A square. Three things are common. So I will take K, Q square by A square common. Okay. And only inside the root, what else will remain? Just think about it. In F1, K Q square by A square is taken out. So don't worry, only 1 is remaining. So 1 square plus in F2, only that number 2 is remaining. So 2 square plus 2 into 1 into 2 into cos 120 is negative half. Is that right? Cos of 120 degrees is negative half. Wow, very good. So what will happen now? Just check this out. 2 cancels. This will become minus 2. This will become minus 2. 2 square is 4. 4 plus 1 is 5. 5 minus 2 is 3. So I'll have root 3 over here. So k q square root 3 and you will have a square over here. That is the answer. That is the answer for your net force acting on that charge q minus q at C. Is that absolutely clear, my dear warriors? How that root of 3 came? Yep. Do we have to take the sign, Kishori? We have already considered the sign by showing the direction. Think about it. How did I realize that F2 is this way? Because I know that both are negative. So if something has been considered, don't consider it again while solving physics problems. Just like when you show that velocity is like this, and you show velocity is like this, then don't write velocity is negative. If I put minus v bar, then it means whatever I've shown is wrong. It is actually on the right hand side. So that's how it works. So same way, my dear students, can you see q and minus q will attract? I've already shown their attraction. So already the angles are marked with the correct signs taken into account and only the magnitudes are shown here. So it's just like a simple vector addition problem. Once I know these are two forces individually, I have to find the resultant force. That's all. Is that okay, everyone? Clear? Oh, shall we go ahead? Shall we go ahead to the next? Okay. Now Coulomb's law in a medium which is other than vacuum. This is very, very again crucial. It will be useful in the next part as well. Okay, and I hope as you're watching this, you're smashing the like button and subscribing to the Vedantu JEE English channel, my dear students. Okay, make sure you're subscribing, make sure you are liking this video. The reason why I ask you to like is obviously it is like a small Guru Dakshina for us, but also at the same time, YouTube understands that you are interested in JEE physics, so it will recommend you more content like that, and it will be helpful for you only. Yeah. If you have vector backlog, cover it right now. Avaneshri, I just made a video, right, on vectors. Where did it go? JEE English channel. I hope you had seen this. Where is it? Vectors. Very simple class. 4-hour class is there. Within 4 hours, you can complete vectors. If you watch this, that's it. And after that, you have to solve problems. Okay. So watch the vectors class. I have also done units and dimensions. It's done. Okay, it's done. Okay, so 2 chapters of 11th are done. Now we are on to, where is it? Now we are on to electrostatics. Tuesday, I'll be doing Gauss law. So this unit of electrostatics and Gauss law is over. And next week, again, second class will be one-dimensional motion, 1D motion. Okay, that's what we are going to focus on. Okay, sure. Where is it? Let's go. Yeah, Coulomb's law. Coulomb's law in a medium other than vacuum. Okay. Yes, definitely you can complete it soon. Now, see, I told you when you have a medium when you have no medium, that is vacuum, then the electrical force of attraction or repulsion is given by 1 by 4 pi epsilon naught q1 q2 divided by r square. This is basically in free space. Nothing is there. It's completely free. But the moment there is some kind of a medium, then what happens? The force changes. It will become 1 by 4 pi epsilon of the medium into q1 q2 divided by r square. This is the force inside the medium. This epsilon m is no longer the permittivity of vacuum. Instead, this is called permittivity of the medium. Permittivity of the medium, which is a medium specific property, like you have density, refractive index, coefficient of friction, etc. These are medium properties, material properties. So any medium has a property called as the permittivity of that medium, which has to be experimentally determined. Okay, it has to be determined by conducting some experiment. Only then you can find it out, and there are tables through which you can get it. In the exam, you are directly given this value, or you are asked to find out by some other information. This epsilon m is actually something called as K into epsilon naught. Epsilon naught is permittivity of free space. This is permittivity of vacuum. A lot of people will think this K is the Coulomb's constant. No, be careful. This symbol is the same, but the meaning is completely different. This K is called as the dielectric constant of the medium. Dielectric constant, dielectric constant of the medium, dielectric constant of that particular medium. Very, very important. So if I substitute it on the next slide and show it to you, do I have a slide? Yes. Okay. So I'll substitute it and show it to you. That new force will become 1 by 4 pi. Instead of epsilon m, I will write it as k times of epsilon naught. K times of epsilon naught. And then the remaining things as it is, q1, q2 divided by r square. But 1 by 4 pi epsilon naught q1, q2 by r square is exactly this force, is exactly that old force, if you notice, is exactly that old force. So why not write it as that old force as it is? This is our new force. And what is it divided by? It is divided by K. So this is also a very, very important relationship. The new force reduces K times. The new force reduces K times exactly than the older force. K is the dielectric constant of the medium. Okay. And this is also very, very important, my dear students. This is also very, very important. The permittivity of the medium is permittivity in free space into the dielectric constant. Okay. So wherever you wrote epsilon naught, it will become epsilon m, basically, of the medium. In general, the force becomes K times less. As simple as that. As simple as that. Very good. Okay, perfect. I put the theory slides also for all of you, just in case if you want to watch it. Let's say if I put a question like this. Example. Okay, this is level 1. Okay. Example. If the force, or rather find the force between 2 coulombs and 3 coulombs kept at 3 meters away in a medium of dielectric constant of 4 question mark. Also, what is the permittivity? Also, what is the permittivity of the medium? That is also the question. Come on, my dear students, try and solve this. Try and solve this quickly. Okay. So very, very simple. All you have to do is simple substitution in the formulas. Oops. Yeah, let's do this. The new force will be, because it's in a medium, instead of 1 by 4 pi epsilon naught, it will be, that constant which will be divided by the dielectric constant. So it is basically 1 by K times of 1 by 4 pi epsilon naught Q1 Q2 divided by R square. This K is not Coulomb's constant. This is dielectric constant, which is 4. This value is 9 into 10 to the power 9. Q1 is 2 coulombs. Q2 is 3 coulombs. Distance 3 meters. So 3 square. 3 square and 9 cancels. 2 and 4 also cancels. It will become 1 by 2. So I think it will become 3 by 2. So 3 by 2 into 10 to the power 9 newtons. That is the answer. That is the force between them. Just check this out. If this is clear, then we'll go to the next part. Yeah, 3 by 2. Yeah, basically 1.5 10 to the power 9. Excellent. Similarly, what about the permittivity of that medium? It will be K times of epsilon naught. K is 4. Epsilon naught is 8.85 into 10 to the power minus 12. Come on. Multiply this 4 times. 8 fours are 32. 85 into 4. Come on. Do this. How much are you getting? How much are you getting? Yes. Come on, my dear students. How much are you getting? 85 is less than 100 by 15. 15 fours are 60. So 0 0.6 less. So it should be 35.4. So 35.4 into 10 to the power minus 12. Just check this out. That is the permittivity of the medium. As simple as that. Yep. Rotational motion will take a lot of time. Yeah, it will come after quite some time, not this month for sure, because we have to go to 1D, then 2D, then Newton's laws and friction, then work energy, circular motion, center of mass, collisions, rotation. Okay, very, very late. It's probably going to come in the month of July end or probably August. Okay, it's going to take some time. We are going to try and complete the syllabus as much as possible by August or September. That's our target. It might go here and there. Obviously, you always need to set a target. Only then we'll start to achieve things. So that is our target, guys. Okay, clear? Let's move now to the next part, which is electrical field intensity. I hope till now whatever I have taught is very nicely embedded in your head. It's stuck in your head and you're learning properly. Okay, let's go to the next part, which is field. Field means any charge around it, it will apply forces on other bodies, other charges using that field. It's like your Wi-Fi signal. Like, I have my phone, it is able to connect to some router or is able to communicate to other phone. How? Through some electromagnetic waves. So this phone applies some effect on some other phone or other telecommunication device. So the charges also wirelessly, they communicate to each other via this field. Please understand, this field is not electromagnetic, it is not gravitational, it is something else only. It's just an hypothetical concept, but it is there. But it is there. Yes. Yes, one. It's going to be beyond April 25 till May. Don't worry. This channel is going to continue. Yeah. Don't worry about it. Just like I hope you saw what and all we did for your seniors. In fact, next year it will be even more. Understand that. Because this year, I was just concentrating mainly on the content and making sure that you have all the kinds of lectures for all these subjects as much as possible. This year, it's going to go beyond the content. It is going to go to more of awareness. It's going to go towards colleges, branches, and so much more. Okay, once we have the content ready on the channel. Okay, already we have a lot of content on the channel, but I want to take the content to a next level. Okay, that's the reason for it. So, electrical field intensity is defined as electrical field intensity is defined as the electric force per unit test positive charge. This is what electrical field intensity is defined as. So just imagine that you have some body. Okay, this is some charged body. This is some charged body. And let's say I want to find the field at this point. To find the field at this particular point. What will I do? I will bring in a test charge. And let's say the test charge is plus 1 coulomb, and on that test charge, I will find out how much force has been applied. It could be this way, depends on what these charges are. It could be even this way, depends on what this system is. For example, I'm just showing it to you over here. The force is example, 30 Newton. Example, it is 30 Newton. then I will say, wait a minute, oh, electric field is force per unit positive charge. So the field on it, the electric field, by the way, the symbol for that is E bar. That electric field is nothing but the force which is there, which is 30 Newton divided by the unit test positive charge, which is plus 1 Coulomb. Hence, the electric field magnitude wise is 30 newtons per Coulomb. 30 newtons per Coulomb. As simple as that. Okay, so this is the magnitude of it. This is the magnitude of it. It is 30 newtons per Coulomb. Everybody, till this point, capacitance, my old videos might be available. Yep. So the by which we define electric field is nothing but the force per unit test positive charge, whatever charge I have placed over here. Electric field is force per unit charge, and you can see the unit of electric field is Newton per Coulomb. Later on, you will also see it is also volt per meter. We'll come to this unit later on. Okay, as simple as that. Also, note one important thing. It is a vector quantity. It is vector quantity in the direction of the force on the positive test charge. Positive test charge. Why positive? It is just a convention. Because somebody will say negative, somebody will say positive. We have to stick to something. That's why we stuck to positive. That's all. Nothing great about it. Okay. So this is the very, very important formula. This is how we define electric field. You can also go one step ahead. One second. Yes, you can also go one step ahead and say, let's say, for example, let's say the electric field is E, and you happen to place a charge over there. You happen to place a charge over there. Then the force which acts on it, the force which acts on it will be nothing but the charge times the field, will be charge times the field. Very, very important. It is the same thing as the previous formula. If you notice, if you shift that Q over here, Q into E is F, Q into E is basically F. That is exactly what you are getting. You can also see that the electric force, and the electric field are in the same direction if Q is positive. If Q is negative, then the force will be opposite. So electric force is parallel to the electric field, if the charge is positive. Makes sense, because if this is a positive charge versus you take a negative charge, if the field is here, you will see the force will also be in the same direction, but the electric force, is anti-parallel, to the field, if the charge is going to be negative, because you are multiplying it with a negative number. Negative times a vector will change the direction of the vector. Positive times a vector will just stretch the vector in the same direction. Negative times will make it opposite. Positive times will keep it in the same direction. That is what it is. Is this absolutely clear, my dear students? These 2 points, why the direction may change or may not change. This is the example of a proton. This is the example of an electron. Yep. Thank you, Divakar. Excellent day. Okay. Okay. Now that we have understood it till this point, we have done this. Okay. Now let's go to the electric field due to a point charge. That is very, very important formula. electric field intensity on a point charge. On a point charge. Sorry, not on, due to. Due to a point charge, my bad. Due to a point charge. So imagine I have a charge capital Q and at some distance r, I want to find what the field is going to look like. So I want to find the field at this point. So I will quickly introduce at this particular point a small test charge which is small q. So immediately I will say electric field is the force acting on that point, upon that charge which is there. So the next step will be nothing but, okay, I'll just put 1 by q as it is. The electric force value will be K between these two, Q divided by R square. Notice how this Q and this Q will get cancelled. This Q and this Q will get cancelled, and I am just left with K capital Q divided by R square. That is your electric field due to a point charge. KQ divided by R square. Is this absolutely clear, my dear students? Is this absolutely clear, my dear students? Also notice one important thing over here is as you go far away, the field reduces. As you go far away, the electric field will definitely reduce, and you can plot it on the graph. So if you plot this field versus distance graph, it will be a curved line because electric field is inversely proportional to the square of the distance. As you go far, the field rapidly reduces and reduces. Clear? Very good. So we can see the same thing over here also, electric field due to a point charge. Now, interesting thing to note is if you are near a positive charge, the electric field on any other positive charge around it will be radially outwards. Does that make sense? Because think about it. If I put a test charge over here, the electric force will be like this. If I put a test charge here, due to this, it will be repulsive. Due to this, it will be repulsive. Due to this, it will be basically repulsive. But here, if I put that positive test charge, it will be attractive. Here, if I put it, it will be attractive. Here, if I put it, it will be attractive. Here, if I put it, it will be attractive. Here, if I put it, it will be attractive. So it is attractive around the negative charge. It is repulsive around the positive charge. So these are the test charges that we place to check the direction of the electric field. Very good. So let's move ahead. And also let me tell you one important thing, that electric field also follows superposition. So electric field also follows superposition principle. There is no doubt about it. Meaning, if I have, let's say a charge over here, let's say I have a charge over here. On that charge, there are many fields. Let's say field 1 is like this. Due to some other thing, it is like this. Due to some other thing, it is like this, and so on and so forth. And there are many such fields, En. So the net electric field, so the net electric field is the vector sum of all the fields. So it will be E1 bar plus E2 bar plus En bar. Okay, so you have to take the vector addition of all of them to find the net electric field. As simple as that. Okay, so let's solve some questions coming up on your screen, and here it is. Two charges are there 20 centimeters apart. The field due to them will be 0. Where? Draw the diagram first. Without that, you will not get anything. Draw the diagram first, only then you will get anything. Okay. Hari and Dharanishwaram, please talk in English. Other students will not understand. Plus English channel for you. Or else then we would have kept quiet with Hindi channel. No. All these years you struggled because you did not have English channels. You have English channel. Use it. Talk in English. Okay. Come on. So we have two charges. One is basically 4 microcoulomb. The distance is 20 centimeter from 9 microcoulomb. Okay. somewhere the electric field will be 0. One thing I know, the positive charges always give the fields radially outwards. So this will try to apply field like this. This will try to apply the field like this. If you notice, here somewhere these two fields will cancel, but if you go here, these two fields will add. If you continue here, again these two fields will add. So they are not going to cancel here. They cannot cancel here because 4 and 9 both give fields in the same direction in this region. Only in this region, this 4 will give the field like this 9 will give the field like this. There is a good chance they will cancel somewhere in between. So I don't know where they are going to cancel. Let's just assume that point, and that distance is x basically. So due to this, the field will be here. Due to this 9, the field will be here. So field due to 4, field due to 9. This is how the directions are. Obviously, the field due to 9 and the field due to 4 should cancel because the net field is 0 at this point. Here, you will see that the net field is 0 because these two fields are cancelling out each other. Due to 9 microcoulomb, what should be the field? By the way, you know this distance. You know this distance. This is basically 20 minus x. This is basically 20 minus x. Okay. So check this out. Field due to a point charge. I just gave you the formula kq by r square. Come on. So field due to 9 will be k. Q is 9 micro divided by r. R is basically 20 minus x centimeters square. That is what it is. Electric field due to the 4 microcoulomb charge. It will be K. Q is 4 micro divided by distance is basically x centimeters and square. You might be wondering, sir, why did you not convert centimeters into meters? Second point, you might be asking, sir, why did you not write 4 microcoulomb or 9 microcoulomb as 4 into 10 to the power minus 6? What is the reason behind it? What is the reason behind that? Think about it. Yes, think about it, my dear students, because I know they are going to get cancelled. Same units on LHS and RHS will anyways get cancelled. So this micro over here, this micro over here, this centimeter here, this centimeter here, anyways get cancelled. So don't bother converting it. Exactly, Kishori. So continuing the journey, what will I get? Even K got cancelled, by the way. 9 by 20 minus x whole square is 4 by x square. Taking roots on both sides, 3 by 20 minus x is equal to 2 by x. Cross multiply, 3x is equal to 40 minus 2x. Take 2x on this side, so it will become 5x is equal to 40. So x will be 40 by 5, which is basically 8. Always in centimeters, everything was in centimeters. So answer is 8 centimeters from the first charge, which is option A. Done and dusted. Very good. Excellent. Yes, Ashwant. Current electricity, it will take some time, Zayed, not so easily. Okay, it's going to take some time. Yeah. Next week, Gauss law. After that week, so next week is Gauss law. After that week will be current electricity. Then we will go to magnetic effects, sources, and all of that. Every week, parallelly, we will be running the show. Okay, moving on to the next one. This question, which was asked in JEE Mains 24, tell me, will you be able to solve it? The same thing has been applied. I just wanted to show you how same type of questions have come in JEE Mains also. Charges Q and 3Q are separated at distance R. The resultant field is 0. The value of x is same type. So this should be done as homework. I want all of you to post the answers in the comment section. Okay, all of you are going to post the answers in the comment section. Now, let's go to the next few geometries, which are again based on the superposition principle, which do not include Gauss law. See, shell, sphere, sheet, line charge, all these geometries I will do in the next lecture because they will be very easy to be done when you learn Gauss's law. So whatever geometries we are learning here are ring and points because they do not need Gauss law. So let's take a charged ring and find the electric field formula. because of a charge ring. Okay, because of a charge ring, guys. So field due to a charged ring. Very interesting. Let's say, for example, I take a ring like this. See if you are able to visualize this ring in 3 dimensions. See if you are able to visualize this ring in 3 dimensions. Okay, this is your probably x-axis. This is probably your x-axis. This is probably your y-axis. This is probably your z-axis, x, y, and z. Are you able to visualize this ring? Yep. Now, um, yes, Surya, I'll be completing kinematics. Kinematics 1D is there next week. Yeah, that's what is going to happen. Now, in this charge ring, okay, if I take the central point, just visualize what will happen to the field. If you are exactly at the center, this is a charge ring. Each charge on the ring will give an electric field like this. You take any charge, it will give an electric field like this. You take any charge, it will give an electric field like this. You take any charge, it will give an electric field like this. You take any charge, it will give an electric field like this. Take any charge, it will give an electric field like this. Now, all these fields are symmetrically distributed. All these fields are distributed in the same plane and they will get cancelled out. Agree or disagree? So what will happen to the net field? At this point, it will be 0. So one thing I think you should agree upon is the electric field at the center is 0 because they get cancelled out because of the diametrically opposite charges. Diametrically opposite charges, the fields will get cancelled out. One thing is very, very clear. But the problem happens if you are not at the center, but at this point. Now, say for example, you take a point over here. You take a point over here. Okay. Let's say, oops. Let's say you take a point over here. Okay. At this particular point, obviously the field will not be 0 because there is some component which will be pending, component which is unbalanced over here. And how to visualize that? I'll tell you what you do. Do one thing, draw a line from any charge to that point. Draw a line from any point on the charge ring to that point. Any point on that charge ring to that point. Any point on that charge ring to that point. Any point on that charge ring to that point. Just visualize this. Is this not becoming like a cone? If I draw all these blue lines, dotted lines, is it not becoming like a cone, my dear students? Is it not becoming like a cone, the curved surface area? Yes or no? Very good. Very good. Excellent. So, my dear students, each of these charges along this line will apply an electric field of their own. So, if I consider a small dq charge over here, a small dq charge over here, okay, d capital Q. Due to that dq, there will be a small electric field like this in this particular direction. There will be a small electric field like this in this particular direction. Okay, and I will call it as dE. And every charge will give the d like that in different directions like this, as if they are on the curved surface of a cone, as if they are on the curved surface of a cone. These dotted lines make their own cone, and the forces, they make another cone in themselves. They make another cone in themselves. Just visualize this. these are the forces, these are the fields. The fields themselves make another cone in themselves. The resultant of all of them, 100% should be in this direction. Should be in this direction because each of the D will have two components. One will be in this direction, one will be in this direction, which I call it as DE in the X direction, and the other one will be the electric field in the Y direction. Electric field in the Y direction. These Y components will cancel. Think about it. One Y will be here, one Y will be here. One Y will be here, the other Y will be here. Other Y will be here, other Y will be here. They will all end up cancelling out each other. They will all end up cancelling all each other. But it is this dx whose integration will give you the net field. When you add these dx, x components of all these small fields, you will get the net electric field. Are you able to visualize this? Give me a thumbs up, then we will go ahead. Give me a thumbs up, we will go ahead. Till this point, is it clear? So what is the value of this d? Well, it is k. Okay, I need this distance also. If this is x and the radius is r, then how much is this distance going to be? It is going to be root of r square plus x square. So it will be k into dq divided by root of r square plus x square, r square plus x square whole square. R square plus x square root whole square, that root will anyways cancel out. I need the x component of it to find the field. So the net field is integral. Just now I told you it is nothing but integral of dEx, which is that electric fields, which is basically this particular electric fields component. Which component will it be? This component. If I take this as theta, it will be nothing but dE cos theta. It will be nothing but dE cos theta. So let's integrate and see what do we get, guys. So integral, what is the value of dE? dE value, I just put it over here. It was k dq divided by r square plus x square. Root has gone. What do you think cos theta is? Well, if you observe carefully, you will realize, this is the radius. This is basically your hypotenuse. The bottom is basically x. If this is theta, obviously even this is theta. Even this angle is theta everywhere. So what is cos theta? What is cos of theta adjacent by hypotenuse? Hypotenuse is root of r square plus x square. So therefore it will be nothing but x divided by root of r square plus x square. Now the best part, k, x, r, everything is constant. Lot of you think I have to integrate this complex thing, but actually no. You will see k is a constant, x is a constant. See, for all these charges, x is the same. Even theta was the same, by the way. These two, when you multiply, you will get r square plus x square whole raised to 3 by 2. What is remaining inside is just the integral of dq. It's just the integral of dq, meaning you add all the charges on the ring. That's it, you will get the total charge. Hence the net electric field will be k q x divided by r square plus x square whole raised to 3 by 2. That is the answer, which is what we had put over here. Kqx divided by r square plus x square whole raised to 3 by 2. Is that clear, everyone? Yep. Cool. Awesome. Is derivation important? Yes. These derivations which I do here are very important, okay, from mains as well as board's point of view. More than mains, I say advanced and board's point of view, it is important. But last year in boards, they did not ask derivations. So it is surprising. So every year, they have different surprises. Obviously, you don't want to keep it till the end. Okay. So that was the electric field due to a uniformly charged ring. And the best part, like I said before, at the center, the electric field is 0. At the center, at x equals to 0, electric field is 0. And also you will see as x becomes very large, then electric field tends towards 0. When you go really, really far away, makes sense, right? I mean, think about it. Why should that happen? Because as you go really, really far away, you are very far away from the ring. The ring will have negligible effects. So the field becomes 0. So that is why the graph of that field first starts from 0, climbs up and again comes close to 0. So it becomes maximum at this distance, which is r by root 2. Remember this value. This comes via maxima minima concept. It becomes maximum at r by root 2. Yes. Is that clear? Okay. Very good. The next important formula that you should know is this one. No need of derivation for this. But anyways, if you want to know the derivation, it is again the same thing. You take dq charge and then because of that you find the field. That field will have two components. The x component will cancel. The y component here will add. Okay. And then you add them via integration with suitable limits. You get this as the answer. So the electric field due to an arc, not a complete ring, but an arc at the center is given by 2k lambda by r sine theta by 2. Theta is the complete angle. You might be wondering what lambda is. Lambda is linear charge density. Linear charge density. It is basically how much charge is there per unit length. The unit of lambda is Coulomb per meter. Coulomb per meter. How much charge is there per unit length? If you take 1 meter, in that how many coulombs are there? That is linear charge density lambda. So 2k, k is Coulomb's constant, lambda by r into sine of theta by 2. As simple as that. As simple as that. Okay. Nothing great about that formula. So let's say for example, you are given a semicircular ring which is charged like this, a semicircular ring which is basically charged like this, and you want to find the field. Because of that, the field will be in this direction. That field by this formula 2k lambda divided by r sine theta by 2. Check what theta is over here. The theta will be 180 degrees or basically pi. So let's say it is also given to you. The charge on it is q and the radius of this is basically r. So what is lambda going to be? Just think about that as well. So theta is basically pi radians. What is lambda? Charge q is distributed on this ring. So charge q is distributed on this semicircular ring. The length of that wire is basically just pi r. Not 2 pi r, just pi r because it is a semicircle. So lambda also I know. So just substitute it and you will get the answer. So it will be 2 times k is basically 1 by 4 pi epsilon naught. Okay, or you can just leave it as k also, no harm. Just see how the options are. Divided by r. Lambda is q divided by pi r and sine of pi by 2. Sine 90 is 1. So this will become 2kq divided by pi r square. That is the answer. 2kq divided by pi r square. Is that okay? Everyone with me? Yes, that is the correct answer. Just direct questions do come on these kind of things. Right. Sometimes you might have a simple, this kind of question also has been repeated many times. Simple question, I'll just show it to you. There was a ring given and the question is at a distance of the radius only, if this is q, this is r, what is the electric field at that point? What is the electric field at that point? So again, you have to use the formula kqx divided by r square plus x square whole raised to 3 by 2. So kq, x is nothing but r. Okay, just substitute r square plus r square whole raised to 3 by 2. So it will be kqr divided by r square raised to 3 by 2 will become r cube. just take that r outside. All right. So if you see, it will become r square whole raised to 3 by 2. What is there inside is 1 plus 1 whole raised to 3 by 2. I just taken r square outside. So this will become r cube. So it will become kqr divided by r cube. This is 1 plus 1, 2. 2 cube. 2 cube is basically 8. 8 raised to half. So it will become kq. R will cancel. It will become r square. Root of 8 is basically 2 root 2. Is basically 2 root 2. So the answer is kq by r square 2 root 2. That's it. Okay, clear everyone? Okay, awesome, awesome. Right, perfect. So these kind of questions, again, standard. Let's complete electric field lines and then we will have a break. We'll complete electric field lines quickly and then we are going to have a break. Okay, these questions are also very straightforward. We'll complete electric field lines before going to the break. Chandrika, this is more than NEET. So this is definitely enough for NEET. In fact, it is more than NEET because we are going to JEE level. Okay, understand that. Now, see, we learned about electric field. Electric field is the force per unit charge. But when I write it down, when I draw it down graphically, those things are called as electric field lines. It's a diagrammatical experience of how the field travels, how the field applies in which direction. So when you draw it, that is called as the electric field lines. And these electric field lines give a sense of what might happen if you place a charge, what direction will it move, where is the effect going to be strong, where is it going to cancel out, where is it going to be attractive. So that idea you get using the electrical field diagram. And these lines which you draw are called as the electrical field lines. So how do those electric field lines look like? Let's see. First of all, imagine you take a positive charge, okay? And you want to see how the electric field lines look like. So what you do is you take a test charge. You take a test charge over there. And you're like, okay, on the test charge, the electric force is like this. Hence, the field will be also in that direction. You move in that direction and place the charge here. Check where is the force. Force is in this direction, but it is not as much as before. It is slightly less. But the field will also be in the same direction. So you continue in the same direction, reach here. Force, again like this, field, same direction. So field is here. Again move in the same direction, reach this point. And you continue doing this as long as it takes. Okay. And that is your electric field line. If you do the same thing over here, the electric force will be here, field will be here, you move by the same amount in the same distance, in the same direction. Again, find the force and the field. In the same direction, move by small amount, see what is the force and the field. In the same direction, continue your journey and you will see this is another electric field line. So these are called as electric field lines. These are called as basically electrical field lines. It so happens that for a positive charge, these electric field lines look something like this, radially outwards. For negative charge, they are radially inwards. For positive, radially outwards. For negative, radially inwards. That is what also I have shown over here also. Positive, radially outwards. Negative, radially, they will be attractive towards each other. If you take just two positive charges, you will see that their net electric field lines look something like this. As if they don't love each other, they hate each other, they will bend. They will basically bend away from each other and it will look something like this. It will look something like this, my dear students. This is how it looks for two positive charges. Whereas if you take two negative charges, and maybe one of them is more negative than the other, then one of them will dominate the other. There will be more field lines from the more negative charge. So probably you're going to see something like this. One field line here, Very few field lines will come from this. Okay, and maybe from here it will be like this. Probably this is what you might see. This is what you might see, something like this. Okay, very, very interesting diagram. One is more negative, so more field lines on it. One is less negative, so less number of field lines on it. So this is how the diagram basically might even look like. Okay, so we'll have more field lines coming onto this negative charge versus this negative charge. This is how it looks like for two positive versus two negative charges. Similarly, if you take one positive and one negative charge, it will look something like this. One positive and let's say one negative charge. Okay, so you will see that the electric field lines will look something like this. They will go from the positive, end at the negative, go from the positive, end at the negative, go from the positive, end at the negative charge. This is how the electric field lines look like. Okay, this is how the electric field lines look like. They'll go like this and they'll come from infinity and they will end over here. So this is how the electric field lines look like for a positive with a negative charge. Two positives, one negative, one more negative. So different diagrams you can make. From looking at all these diagrams, what do you feel like? These field lines never ever intersect. Definitely, they never ever intersect. They never mingle with each other's affairs. They are never intersecting. Also, they are crowding at some places. They are not crowding at some other places. You can also see as if these field lines itself don't love each other. They try to, stay away from each other. And also, you can see they hate each other so much that they never ever intersect. They never ever intersect no matter what. They always start from the positive charge and they end at the negative charge. They always start at positive and end at negative. Wherever they are crowded, the field is very strong, whereas where they are less crowded here, or let's say here less crowded, the field is very, very weak. Here also, there are no field lines here, so the field is very weak in this region, but maybe here or close to here or here, the field is very, very strong. That is the sense that you get. These are exactly the properties of electrical field lines. Electric field lines are hypothetical lines, imaginary lines. You cannot see them in reality. Yes, you can sprinkle few things here and there and get an idea of the field lines, but you can never ever see the actual field line because they are only a concept to understand other things. The tangent drawn gives the direction of the field, kind of makes sense also. Okay, if I draw a tangent to this, it gives me the direction of the field. No two field lines will ever intersect. The crowding represents the field is strong. They must originate from positive and they must terminate at negative. They cannot intersect and they cannot form closed loop, meaning it's not like the field lines start and end at the same point. This is a closed loop. This does not happen. They always start from positive or infinity and they end at negative or even at infinity, because you can see over here they started at positive, ended at infinity. Here they started at infinity, ended at negative. These are the only possibilities. Is that clear? Okay, is that clear? Wire and other things, remember, we will be doing it in Gauss law, long wires. Okay, in Gauss law, we will be doing those geometries, not over here. Great. Now that you understand these properties, I don't know why this diagram got duplicated. So remember, if I have electrical field lines like this, here it is going to be strong field, here it is going to be a weak field, and by chance somebody puts a charge maybe somewhere over here, then that charge will experience a tangential force and that force will be charged into the field, okay, along the tangent. That is what it will be. So using this, let's do some questions coming up on your screen. Wow, directly level 2 JEE Mains question. I think we should be able to do it. Suppose a charge wall is already giving a uniform field Now, what is the meaning of uniform field? You should also understand this. See, this one, the diagram that I have drawn over here is non-uniform. This is non-uniform field. But imagine the electric field lines were parallel to each other. That means the electric field is constant. This is called as a uniform field. This is called as a uniform field if the field lines are just parallel and equally spaced. Here the spacing is not the same. So now it's a uniform field. The charged particle is being suspended through a silk thread and remains at a distance of 10. What is the charge on the particle? This was asked this year, JEE means 2024. Shirish, even if you remember the end results, it's okay. These end results, yes, it's going to do your job for JEE mains. For JEE advance, no. Hello, SK Talks. Okay. Thank you, movie clips. Thank you so much. Thank you so much. Hello, Jayesh Shanmugam. Hello, Jayesh. Okay. So let's draw the diagram first. So we have electric field, which is very, very strong. And that is 2 into 10 to the power 4 Newton per Coulomb. I'm just showing it in a very dark color because I don't need to see it for a long time. A charged particle of mass 2 grams is being suspended through a silk thread and remains in equilibrium at 10 centimeters from the wall. Beware, this is our wall. This is our wall creating that electric field, and there is a thread like so, like this, and this distance is 10 centimeters. This is 10 centimeters. The thread length 20 centimeters. The thread length 20 centimeters, and it is staying intact in equilibrium. So what might be happening? Think about it. 100% there is an electric force in this direction. That force is Q into E. That force is Q into E. Another force is the weight of the object, and that weight will be nothing but M into G. Another force is basically the tension force in the string. So that tension will be here. These are the only three forces acting on the charged particle which is suspended, and it is in equilibrium. So all the forces must cancel each other. Okay. One more thing which I would love to tell you is if I continue with this vertical line and maybe start marking the angles, things will be even more apparent. If I mark this as theta, these two gray lines are parallel to each other. So this will also be theta. And I think I know what theta is. If I do sine theta, just check this out. What is sine theta? Sine theta is opposite by hypotenuse. This is 90 degree. So it will be 10 by 20, which is half. So therefore, theta is 30 degree. So with the wall, it is making 30 degrees. That's the first thing that we got. Good evening, anime gods. Good evening, Nan Patinam. Wow, nice name you got. Okay. Now, if this much is clear, the tension will have two components. The vertical component cancels the weight, and the horizontal component cancels the electric force over there. So therefore, can I say in the y direction versus in the x direction? So let's start with x first. So t sine theta, right? This is t cos, this is t far away, far means sine, is nothing but the electric force, which is basically QE. In the y direction, the t cos theta, the tensions cos is close, so is equal to mg. I don't know the tension, no issues. Let me divide the two. So I will get sine theta by cos theta is QE divided by mg. What do I need to find? The charge on the particle. So I just need to find Q. So this will become tan theta. So tan theta, mg goes over here, and electric field comes down over here, is basically the charge. Perfect. So the charge value will be mg tan theta. M, you know how much is it? 2 grams. So 2 into 10 to the power minus 3 multiplied by g value, which is basically 10, into tan theta. Tan 30 is 1 by root 3. So root 3 will come below. Root 3 will come below because tan 30. Electric field is 2 into 10 to the power 2 into 10 to the power 4. Perfect. So what is the value of Q? 2 cancels. 10 raised to minus 3 into 10 will become 10 raised to minus 2. 10 raised to minus 6. So 1 by root 3 into 10 to the power minus 6 coulombs, which is 1 by root 3 microcoulombs. So hence the value of X should be 3. Answer is 3. Perfect. We got the answer. Is that clear? What is X? X is what has to be found. Okay, Hadiksha, we have to find X. Sir, tan theta is the 2kq by mgl, sir. 2kq by, no, I don't even have to find that kqq by r square because this is not the electric force between two charges. I already have been given the field. If I know the field, I can find the force by multiplying the field with the charge. That's why I did not use that Coulomb's constant formula, kqq by r square. That is not needed because field is already given to me. So I just substituted that. Is that okay? Fair enough? Yeah. Sudarshan, both have different purposes. Physics Galaxy is mainly advanced to Olympiads level. So it is completely advanced to Olympiad levels. Okay, that is what Physics Galaxy's purpose is. Tatva is from basics to advanced. Okay, so the range only is different. What exams are you targeting and what confidence you have, which book you already have, and what can you afford, not price wise, but confidence wise. It should not happen you start with Physics Galaxy and lose confidence, or you should not be like you're solving Tatva and you're like, okay, I'm able to solve. Okay, initial problems are easy and I have advanced level questions also, but I want to solve Olympiad. Then you will lack that. So the purpose of the books are completely different. Okay, right. So this is done. This is done. Let's see if you have some other question. Wow, we have another question coming up. Looks complex, level 3 question. But before we head the break, I think we should solve a level 3 question. But I feel this is much easier than level 2. Or maybe the level 2 should have been level 3. Okay, come. Let's see if we can solve this. Let's see if we can solve this. A charged particle enters a point A, okay, it enters a point A, comes out from point B, maybe because of the electric field, it is going in a curved path, something like this. Okay, it is going in a curved path, something like this. I'm just showing some random thing. Okay, this might not be the actual path, chumma, I'm showing some random path. The fields are in the vertical direction from positive to negative. Kinetic energy at the 2 points ratio will be how much? Okay, interesting. Okay, see guys, if the field is vertical, where will the force be at any point? Always vertical. It's an charged particle. Okay, always vertical. So the electric force will always be in the direction of y-axis. So if I say the force is along y always, if I ask you what is the x component of the force, the answer will be 0. So what is the acceleration in the x direction? 0. So what is the velocity in the x direction? Oh, don't say 0, just say it is constant. Just say it is constant. So at this point and this point, the velocities are going to have two components. One is over here. So this component will be like this, and another component will be like this, and here also will have one component like this and one component like this, maybe. So over here, if you see what is the x component of the velocity, let's say it will be u cos alpha, sorry, sine alpha, my bad, u sine alpha. Why sine alpha? Because if this is alpha, even this is also alpha. So the red one will be cos, the green one will be sine. Over here, when you reach, the velocity could be something else. So maybe it is v, maybe it is v sine beta. So if this is V, this is V cos, this is V sin, red one will be V cos. So definitely these should be equal. So U sin alpha will be V sin beta. So sin alpha, alpha is given to be 60. Beta is given to be 30. So therefore, what do I get is sin 60 is root 3 by 2. Sin 30 is half. 2 cancels. Therefore, basically V by U is basically root 3. What do I do with this? Well, check this out. We want KB by KA. So KB by KA is half M. At this point, what is the speed? V square upon half M. At A point, what is the speed? It is U. So M 2 cancels. I am just left with V by U whole square. But V by U is root 3. So just put root 3 and square it. So the answer is 3 for this particular question, which is the case. Is that clear? Very interesting question. A lot of people think there is some electrostatics involved, but actually more than electrostatics, the concept is of mechanics and kinematics and vectors. You will see electric force is always vertical, so it has no contribution in the x. It's like gravity. Gravity acts in vertical, so it does not change the horizontal velocity. So the horizontal velocity is constant. So at this point, velocity is u, here it is v, this is v sine, this is u sine. That's it. So these two sine components are equal. Solving this, we get the ratio of the speeds. Dividing the kinetic energies, substituting, you get the ratio which is required. Is that clear, my dear warriors? Is that clear? Okay. So now before going on to electric potential, we will take a break. Okay, we'll take a break. So, and then complete the remaining things. So this is break time. We will return. We'll return at 7:50 p.m. Okay, 7:50. Oh, this is not 7:50, 7:45. So 7:45 p.m. Okay, so 7:25. So take a 20-minute break. Hello, hello, hello. Hello, everybody. Let me know if I'm audible and visible. Yes, call all your friends, message on the groups, whatever WhatsApp groups, friends groups. Yes, send them message. Shreyas sir is live, and you should also share it in your status on your social media that Roar series is going on for all of us. Yep, you need to put it up in your communities, in your WhatsApp groups, Telegram groups, wherever you are. Okay, so let's begin, my dear students. Let's begin. Let's begin. Okay, so let me pull up the chats properly. Okay, all right, cool. So let's start with the term electric potential now. We are done with electric field. We are done with electric field lines. We are done with force. So potential energy, and dipole. These are the few things which are remaining. Now, just like you had field around any charge, there is also potential around any charge or system of charges. When I say that there is potential around a charge, means there is ability to store energy if a charge was placed. And let me explain this to you with a simple concept. Imagine, imagine, you know, there is a there is a teacher, there is a teacher, okay, and uh, some coaching, some institute, some classroom, whatever. And maybe there are some benches around that teacher. Maybe there are some benches around that teacher. Over here, these are some vacant spots. Some batch is being launched, new batch for J25. There are some vacant positions. So this teacher has ability to teach some students and has some vacancies in that particular classroom. So these vacancies is basically something like, the ability of the teacher to fill up that classroom, to teach those students, to mentor those students properly. You know, it's something like that. When you actually fill up these seats with some students, when you actually fill up these seats with some students, okay, so now this batch is full, students are completely filled in this particular classroom, then that is very similar to potential energy. That is very similar to the term potential energy. So same way, just like the teacher, replace it with, you know, charge or charges. This is nothing but a charged body, just like the teacher. You stand anywhere near the charge, you will have potential. You will have potential. That means you have ability. You have ability, or you are capable. You are capable. Capable of what? You are capable of gaining energy. So that students which fill up that vacancy, that point, that student is like that charge which will come over there. And once that charge is there, then that charge along with this charged body together will have energy, and because it is of potential, that is why potential potential energy, that is why that system will get potential energy. Do you now understand the main difference between potential and potential energy? Potential is before placing the charge near that body. Potential energy is what that system gets after placing the charge. Potential energy has a symbol capital U. Potential, by the way, has a symbol capital V. Potential energy will be measured in joules, whereas this potential will be measured in joules per coulomb. Joules per coulomb. That is what it is. Everyone, till this point, is it clear? Everybody, till this point, is it clear? Yeah. Exactly. I want everyone, Sadhana, Dhirish, uh, Dhiren Nishwaran. Yes, Adiksha, please chat in English. Please chat in English, okay? So that even I will understand, others will understand. A lot of Telugu students are there, a lot of Tamil students are there. Imagine how it will be if Telugu students talking Telugu, Tamil students talking Tamil, Hindi students talking in Hindi. How will it be? It will not be good, right? So make sure you are talking in English. And if others are also there, I know you love talking in your local language, but try to, yeah, talk in English over here. Okay, great. So potential is basically, at any point is the formal way of defining is the work done to bring an external, a unit positive charge from infinity to that particular point. Infinity to that particular point. That's the formal definition of it. It's a scalar quantity because energy, joules, all these things are scalars. They are not having any direction. There is no meaning of what is the potential in that direction, what is the potential in this direction. No meaning at all. So it is a scalar quantity. SI unit is volts. Also, you will see the other unit is joules per coulomb. Both are the correct units. We also assume potential to be zero at infinity. Now, why is this important? Is because, see, whenever you measure potential, you always compare it with something. Like you are more intelligent or you are intelligent. When I say you are intelligent, that means you are comparing it with someone. There is a set of people and you feel that as compared to them, you are probably intelligent, but the same person in maybe some very toppers class might not be so intelligent. He might seem to be not that great, maybe just an average student. So same way, guys, potential always is compared with respect to something. So we assume that when you are very, 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 very far away, when you do not see any other charge, you're infinite distance away from all the things around you, then the potential is assumed to be zero. So infinity is assumed to be as a standard reference point where the potential is zero. So that is what has been mentioned right over here. Is that clear, my dear students? Yep. Is it clear, my dear students? Okay. All right. All right. How to prepare for JEE Mains 2024? Impana Music has asked, Sir, can you give me tips to prepare for JEE Mains 2024? So I'll tell you, it's very simple. First step is you have to buy a time machine. Okay, you have to buy a time machine. Then you have to go back in time at least some few months. At least go to 2023. 2023. And in 2023, watch a strategy video of how to prepare for JEE Mains for 1 year. 1 year, and then attempt the 2024 JEE Mains paper. Okay, and then you will get a good college. So very simple steps on how to clear JEE Mains 2024. Okay, now moving ahead, let me formally define potential. So let's say you are taking this particular point, uh, infinity. This is infinity. At infinity, the potential is assumed to be zero. This is also called as the zero reference. Zero reference. And from infinity, I take that charge q and bring it at this point. There is some work done in this particular manner. So that work done per unit charge is basically defined as the potential at that particular point. The potential at that particular point. And this work done is from infinity to that particular point. So that's why it is also sometimes written down like this: from infinity to that particular point, dw is the small work done. But please bear this in mind. This is by the external force. A lot of people make a mistake here. This external force, all right, this word, many people miss that. So it's the work done by the external force upon the charge which has been brought over there till that particular point, that gives you the voltage. Okay, so this is a mathematical way of writing it. This is the mathematical way of basically writing it. Excellent. Excellent. Very good. Awesome. Awesome. Okay. Now, once this is understood, you have the electric potential due to a point charge. Electric potential due to a point charge, which is the standard formula. If you have charge Q and you are standing at a distance r from it, what is the potential? What is the potential at this particular point? So to find that out, again, what is generally done is you take another test charge and you bring it from infinity to that particular point over here and calculate the work done, and that's it. You will get the potential at that particular point. So the potential at that particular point, using our definition, is integral dw from infinity to that point by that external force upon that charge. So when you do this infinity to that point, the work done is nothing but the external force external force which is required dot that displacement. I can also call it as dx or dr or whatever you want to call it, upon q. And this external force which will be needed will be k q and then small q divided by, at any random point it will be basically x square. And the final limit to this will be basically r. The final limit to this will basically be r. So you calculate this work done, and the formula that you get is nothing but kq divided by r. kq divided by r, that is the potential due to a point charge. That is the potential due to a point charge, at a distance of r. K is Coulomb's constant, q is that charge divided by the distance where you are calculating the potential. As simple as that. Okay. So this formula, again, very, very useful for all of you for solving many problems. In fact, you will find problems like this, where you might have multiple charges, Q1, Q2, Q3, Q4, Q5, Q6, Q7, like that. And due to each charge, there might be a potential at this point. So when you add the potentials due to all the charges, potential due to this charge, potential due to this charge, you add them, you will get the total potential at this point. And the best part is you don't have to worry about the direction, because potential is a scalar quantity. So the best part is you just simply add their magnitudes with the signs. Of course, some of them might be positive, some might be negative. So you add them with the signs, you will simply get the voltage at that particular point. So this is again an extension of superposition. Remember, if this was a problem of electric field, then each field will be in different directions. You had to do the vector sum to find the net electric field. But for potential, that's not the case. You just have to simply add the values of the potentials. Is that absolutely clear? Is that absolutely clear? Yes, everyone with me? Great. Now, also keep this in mind. It is quite possible that at particular point number 1, you might have potential 1, at other point you might have potential 2, and then between these 2 points, you will get the thing called as the potential difference. This is basically your potential difference. Potential difference. Potential difference. And very, very important is, it doesn't matter which path I take, whether I go via this path or I go via this path, really doesn't matter, is independent of the path, is independent of the path. And why is it so? Whether you go this path number 1 or path number 2, is because since electric field is conservative in nature, electric field is conservative in nature, and conservative forces have that property that you don't have to worry about the path, as long as your initial and final path points are same. No matter how you reach the destination, as long as the source and the destination are same, the work done will be the same. So potential difference will also be the same. So potential difference will also be the same. So this is something which you need to know. Also keep in mind the units of potential. Where is it coming as joules per coulomb and all of that. So if I do 1 joule of work to bringing a charge from infinity to that point, in bringing 1 coulomb of charge, the voltage at that point is said to be 1 volt. The voltage at that point is said to be 1 volt. That is why you will see 1 volt is 1 joule per coulomb. That is how it has been defined. So if I do 1 joule of work in bringing 1 coulomb of charge from infinity to that point, then at that point the potential is 1 volt. That is what the meaning of this statement is. Is that absolutely clear? Okay. So these are some important things regarding potential. So I think it's a good time that we start with some questions as on the screen. A cube of side B has a charge Q at each of its vertices. Determine the potential and the electric field due to this array at the center of the cube. One of the answers is easy, one of the answers is lengthy. Can you think and tell me which answer is lengthy, which answer is easy in this? It's a cube after all. Let's think about it. Cube. All right, this is the cube. And where are the charges? The charges are on the each of the vertices. So there are, remember, 8 vertices. All the 8 vertices, the charges are there. All the 8 vertices, the same charge Q is there. And the side length is B. Side length is B. So if you are at the center of the cube is somewhere here. Try to visualize that. The center of the cube will be somewhere over here. So basically just try to draw the diagonals. Probably that will make it very easy for you to understand. So I'll just try my best to draw the diagonals. Somewhere over here. Yeah, so if you draw all the diagonals, you can see where it is meeting. So that is basically the center. That is basically the center of the cube. Are you able to visualize this? Are you able to visualize this? Yep. So now think and tell me, yes, which of them is easy? Potential is easy, wrong. Field is easy. Field will cancel. In fact, the electric field's answer is big fat 0. Where is it? The electric field, yes, this one will cancel. All the fields will cancel. All of them will cancel due to all of them. Hence, the net electric field will be a big fat 0. That's the direct answer. Because of this charge and this charge, opposite, all opposite charges, the fields will cancel. The main problem is with the potential, and the good part about the potential, see, I know it is little lengthy, but the good part is, first of all, it is scalar. So I just have to worry about the magnitude. That's it. Number two, this point is equidistant from all the vertices. This to this, this to this, this to this, this to this. So if you take any diagonal, so my dear students, if you take the diagonal and this point is at the exact center, like you can see, what is the length of the diagonal? What is the length of the diagonal? The diagonal length of any cube is basically the side length times root 3. The side length is b, so it is b root 3. If that is the diagonal, what is the distance between this green dot and the blue dot? What is the distance between that green dot and that blue dot? Let's say I call it as d. That distance d is the diagonal divided by 2. It's exactly the midpoint. It's exactly the midpoint. So it will be b divided by 2, and this is root 3. Why is that important? Is because the charge that you are talking about Q is over here, here, and so many other places, and you want to find the potential at this point due to all the charges. So when I try to find the total potential, it will be, there are 1, 2, 3, 4, 5, 6, 7, 8, 8 charges into potential due to each charge. So it will be 8 times k q divided by this distance, which is d. This distance, which is basically d. So it will be 8kq divided by distance, which is basically b root 3 divided by 2. So that 2 gets multiplied. So it will just become 16kq divided by b root 3. That is the answer. 16kq by b root 3. 16kq by b root 3. Exactly the same thing. And the field value will be 0. The field value will be 0. Perfect. We got it. Yes. Is that clear, everyone? Everybody clear? Awesome. Awesome. Keep this in mind. Okay. Everyone clear about this? Everyone? Awesome. Chalo. Let's go to the next question coming up on your screen then. Let's go to the next question coming up on your screen. Okay. Chalo. Let's go. What is it? Wow. Electric potential. J means 2023 question. Electric potential at the center of the two concentric half rings. We did a question on half ring, but that was on the field. Now they have asked a question on the potential. Interesting. Question is, what is the potential at the center? Lambda are the linear charge density. Lambda is the linear charge density. Okay. Capacitance in a separate chapter. Capacitance is going to be in a separate chapter. See guys, first of all, let me tell you one thing. When you have a semicircular ring and you want to find the potential here, the best part is all the charges on the ring are at the same distance. And I don't have to worry about the directions. So if you take any charge, it's at the same distance. So when I try to find the total potential, which is summation k q divided by the radius, k and r are constants, they will come outside. I will just have summation of the charges, which is basically the total charge on the ring, But if I write it in terms of lambda, remember lambda is how much charge is there per unit length. The charge on the ring is capital Q. The length is the semicircle circumference, which is pi r, not 2 pi r. 2 pi r is for the circle. So that is lambda. So rearranging this, I will get Q is equal to pi lambda r. Substituting pi lambda r over here. So I will get K divided by R. Instead of Q, I am putting pi lambda R. RR will get cancelled and I will have K lambda pi. K lambda pi. If you want, I can substitute the value of K also. It will be 1 by 4 pi epsilon naught lambda pi. Pi by. So I will just have lambda by 4 epsilon naught. Lambda by 4 epsilon naught is the potential due to a semicircular ring. This derivation I will have to do on the spot in the rough book. Without that, I will not be able to do. Okay, so now going back to this, there are two rings. Oh, the best part, it is independent. It is independent of R1 or basically R, the radius. So means this R1 and R2 is useless. That's why you see in the options, it's not there, number one. Number two, in the question, it is not given. So that's the best part about it. So when I try to find the total net potential due to ring 1 plus potential due to ring 2, just go to this formula. Lambda by 4 epsilon naught. Lambda by 4 epsilon naught. Both have lambda only. So lambda by 4 epsilon naught. 1/4 plus 1/4 is half. So lambda by 2 epsilon naught, which is option A. Let's check it out. Yes or no. Yes, it is the correct answer. It is the correct answer. Lambda by 2 epsilon naught. Is that clear, my dear students? Yep. Shall we go ahead? Shall we go ahead to the next one? Okay, let's go. Let's go. Let's go. Let's go. Let's go. Let's go. What do we have? Electric charge is placed. J means 2024 this year. Is placed at the origin, and 2 points are situated, and so and so. The difference of the potential between P and Q is. Okay, let's understand this. P and Q, X and Y axis will need. This is X, this is Y. P is root 3, root 3. So this is root 3, root 3. And Q is root 6, 0. So Q is basically root 6, comma 0. Question is, what is the voltage difference between these 2 points? To find that, first, what is the potential at point P? We need this distance. So if I find RP, RP will be root of root 3 square plus root 3 square, which is 3 plus 3, which is 6, root 6. If I ask you what is this distance, RQ, well, that is directly root 6. Oh, wait a minute. RP and RQ are same. So RQ is equal to RP, which means the voltage at point P will be equal to the voltage at point Q. So if you ask me what is the voltage difference between the points P and Q, the answer will be a big fat 0, which is C. Let's check it out. Yes, it is correct. The answer is going to be C because the distances are same. The distances are same. Is that clear, everyone? Shall we move ahead? Loving the session, understanding potential. We are solving all kinds of questions, varieties of questions just for you. When you talk about a charged ring and you want to find the potential, this job is much, much easier for a ring for potential because you don't have to worry about the direction. Because you don't have to worry about the direction, my dear students. So, if you take any charge on the ring from that point where you want to find the potential, this distance of r square plus x square is same for all charges on the ring. All charges on the ring. If I call this as small r, and if I call the charge over here as dq, then at this particular point, when I try to find the voltage, it will be integration of all the small voltages due to all the small dq charges. So each dv will be k dq divided by the distance, which is basically r, but k and r are same for all the charges. So bring that r outside, and what remains inside the integral is just dq. dq's integration means I'm summing up all the charges here, which is just going to be capital Q, and this comes over here as it is. That's it. So it is kq divided by small r, but small r is that formula which I have just substituted here. So hence the total voltage will be kq divided by root of r square plus x square. So this is the formula. This is the formula for a ring which is charged to find the voltage. Kq divided by root r square plus x square. Is this clear? Understood? Why is it simple? Is this simple? Okay. Very good. Very good. All right. All right. Now, yeah, this is done. Now we have to go to electrical potential energy. So let's go to electrical potential energy now. We have done with potential. So let's start with potential energy. So what is potential energy electrical? So imagine this is your universe, which you basically can also say that this is infinity. This is your universe, and this is like a playground, and all the players are outside the playground. The playground is the universe. to get the players inside the playground, you need to pay a lot of money to them. Correct? Only then, IPL auctions, they will play on the ground, or else they have no motivation. So same way, imagine there are many charges, 1, 2, 3, 4, etc. Q1, Q2, Q3, etc. Q3, Qn. These charges right now are completely unaware of each other because they are outside the universe. They are so far away. Outside means very, very far away. They don't know they exist. It's like your far off relative, your mom's, uncles, sons, again, some daughter-in-laws, some cousins, mothers, brothers, something, something. You don't even know they exist. Now you bring all these family members together, you bring all these cricketers on the playground, and eventually you place these charges Q1, Q2, Q3, Q4, like that. Over here, you have assembled them like a family gathering. Somebody's wedding is there. All these family relatives, everyone, they have come together for that particular function. They have assembled, you have arranged them, together. Okay, they are all interacting with each other. Oh, hello, you know what, I'm that mamas, that that fathers, this sons, this brother, this cousin, this daughter-in-law, blah 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 blah. They're interacting with each other. So when you do this process, you have done some work. That work done to assemble them is called as the potential energy. Very simple. So electrical potential energy, by the way, the symbol is capital U, is nothing but the work done to simply assemble the charges. Assemble the charges. That's it. Assemble the charges. And this is nothing but integral. Again, dw, but do not divide by any charge. Just infinity to the points or the location where you want to keep them. From infinity to the location where you want to keep them. Also bear this in mind, when their separation is infinity, it is assumed to as 0. They have no potential energy when they are really, really far away. That is also termed as the zero reference. Zero reference. That is called as zero reference energy. That means they do not know the other charges exist, and their energy is taken as a baseline, as a reference, as 0. You compare everything with respect to this. You compare everything with respect to this particular potential energy. Okay, so this is the true way of defining potential energy. When you divide it with charge, what you get is potential. When you divide it with charge, what you get is potential. Exactly. Okay. Yes, Survesh Raj, Tatva contains JEE mains PYQs in a separate exercise, JEE advanced PYQs in a separate exercise. Okay, I hope this is clear. Okay, okay. Chalo, let's continue. If now you happen to take two charges, what is the energy of such a system to assemble them? So it's like only two people. It's like Pandu Champa. Before me, Pandu Champa never existed, or Pandu did not know about Champa. Champa did not know about Pandu. But thanks to your Shreyas sir, Pandu got to know about Champa. Champa got to know about Pandu. So charge 1 and charge 2 were really far. They got to know about each other. They were brought together, and to assemble them, I did some work. That work is K Q1 Q2 by R. That work to assemble them together is K Q1 Q2 divided by R. So then you might be wondering, sir, what if there are more charges? Well, the answer is very simple. Let's say there are 3 charges. Then what will happen? These two will have an energy K Q1 Q2 divided by R12. These two charges will have K Q2 Q3 divided by the distance R23. These two charges will have K Q1 Q3 divided by the distance between them, which is R13. Perfect. So now what if there are even more charges? Even more charges. Well, answer is simple. You find the energy with this, 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 with this, with this, with this, with this. What else is there? Even this, even this, or even this, all this, basically all combinations. That's all. So whenever there are multiple charges, the potential energy of the system, is K, Qi, Qj, Qj, Q1, Q2, Q2, Q3, Q4, Q7, Q8, Q5, Q5, Q3, Q2, Q7, like that, divided by the distances between the respective charges, but the summation of that. So that's why I will have to put a symbol over here. I'll have to put a symbol over here like this. But the catch is I should never be equal to J. I should never be equal to J. So you try out all the combinations. Okay, I should never be equal to J. As simple as that. You should not repeat it. Is that straightforward, my dear students? Yeah. Sir, for the exams, would it be better to solve PYQs or in NCRT? Ishan, for JEE, it is better to solve PYQs, not NCRT in text. NCRT in text is okay for CBSE level, but for JEE level, don't go with NCRT in text. You have to go much more beyond that. It's of no use. Even for NEET these days, just solving NCRT in text questions is of no use. There are a couple of cases where they use those questions, but that is very few, not like out of 50 questions, the 40 questions are from them. From 50 questions, maybe 2 or 3 questions might come from there, maximum. That too after changing the values. So PYQs is a better option, not NCRT in text. Okay. So now that you know about this, let's go ahead and solve some questions. Three particles, each of having 10 microcoulombs, are placed at the corners of a triangle. The electrical energy of the system is how much? Let's draw a triangle first. And three particles are there. Of 10 microcoulomb. Okay, 10 microcoulomb at the corners of side 10 centimeters. So the side length is 10 centimeters. Question is, find the energy of the system. Now, when I try to find the potential energy of the system, understand there will be three terms. This guy with this guy, this guy's energy with this guy, this guy's energy with this guy. So there will be three terms, and the best part is all the charges are equal, the distances are also equal. So I will have 3 times the energy between each pair of charges. 3 into what is energy between each pair? It will be K, Q, Q divided by distance square. No, distance only, no square. So it will be 3 into K is basically 9 into 10 to the power 9. Charges are 10 micro. So 10 into 10 to the power minus 6. 2 times, so square, divided by the distance, which is 10 centimeter, which is basically 0.1. So my dear students, what will happen? 9 threes are 27. That's it. 27 into all these other terms. Just check it out. What will it be? 10 raised to minus 6 into 10 will make it 10 to the power minus 5. Whole square will make it 10 to the power minus 10. Minus 10 into 10 to the power 9 will make it 10 to the power minus 1, which is 0.1. 0.1 and 0.1 will cancel. So just check this out. This will become 10 to the power 9 into 10 to the power minus 10 divided by 0.1 is 10 to the power minus 1. This whole thing will just become 27. Which is option C. Yes, that is the correct option. Very good, Divakar, Adiksha, awesome. Hello, Supriya, I'll watch your class recorded. No issues. Ruhika, I'll be starting current electricity after 1 more week. Next week, Gauss law, motion in 1D. After that, current electricity. Make sense? Okay, cool. Shall we go ahead to the next question on your screen? Two charges are fixed as shown, and a particle of some mass is released here, and it is on a frictionless plane. This is a horizontal plane. It's not vertical. Gravity has no effect. Find the speed as it reaches the origin. It's an interesting problem if you notice. See, this charge Q2 and this charge Q1 are how much? Q1 and Q2 both are positive. Both are basically positive. So let's put it over here. This is also positive and this is also positive charge. Both are 2 microcoulomb. 2 microcoulomb. Then you have a negative charge over here. How much is that? It is minus 4 microcoulomb. So this will be attracted by both of them. It will accelerate, and after some time, this charge, after some time, you will see that this particular charge would have, achieved some speed as it reaches over here, at the origin. So the question is, what is that particular speed? So think of it this way. When it was here, it had no kinetic energy. When it is here, it has some kinetic energy. Where did it gain that kinetic energy from? It can only come from one thing: electrical potential energy. So maybe here there was some energy, here there was some energy. That energy has been deferred by some value. Maybe potential energy was lost, and that's why kinetic energy has been gained. So just use energy conservation. So if I use, simply put, energy conservation, initial potential energy plus initial kinetic energy is final potential energy plus final kinetic energy. Initial potential energy, think about it. Think about it, my dear warriors. Think about it, my dear warriors, what that initial potential energy would be. This charge with this charge, this charge with this charge. By the way, this is minus 3, this is 4. So obviously this is 5 meters. This is also 5 meters. So the energy of this guy with this guy, energy of this guy with this guy will be how much? Just check this out. It will be K Q2, Q3, which is, I will call Q2 and Q1 as Q, that will be better. Q1 and Q2. Okay, I'll just call it as Q, guys, that will be better. So Q into Q3, Q into Q3 divided by that distance, which is basically 5. But there are two such charges, this with this with this. So into 2 times, into 2 times. Now, another energy is also there between this guy and this guy, but I will not count it. Reason, because when I complete this equation and I write kinetic energy is 0, because here it was at rest, of course, and I write energy again over here, understand that these two charges will still have the same energy. These two positive charges will still have the same energy. Whatever is the energy between Q1, Q2 will remain the same. Only this charge is moving. So if I put it here, I'll put it here. They will anyways get cancelled. So for the sake of your understanding, I'll just put it over here, plus K Q2 Q3 plus K Q2 Q3, both Q2 Q3 I have assumed, Q2 Q1, sorry, it is assumed as Q only. So K QQ divided by the distance. That distance is going to remain the same. So don't worry only about it. Don't worry about it. Kinetic energy initially is 0. This is equal to final energy. Final energy, again, these two charges will have the same energy. These two charges will have the same energy. So KQQ by D. Do you notice that this term anyways gets cancelled anyways? It gets cancelled anyways. So now when you reach here, my dear students, this charge has come over here. This Q3 charge has come over here. What is the energy between Q3 and Q2? Q3 and Q1? Well, that will be K Q3 into Q2. Q2 and Q1 both are Q. So Q into Q3 divided by this distance, which is basically 3. But this energy and this energy, two separate. This with this with this. So into 2 times. And it also has kinetic energy. So half m v square and half m v square. So that is the kinetic energy. Potential energy is this, but this part and this part anyways gets cancelled. Do you understand it? Yep. At the beginning, what to do for solving the problem? Karthik, analyze what is happening, why is it moving, which law, which theorem, which property, which conservation, what will help you? Here I understood that because it is accelerating and it is gaining some energy, forces will be difficult because force will continuously change the angle and the magnitude. Energy will be easy because here the gain of the energy kinetic wise is coming from the difference of the potential energy. So initially there is some potential energy of this entire system. One term, one term, one term. Three terms are there. Two terms here and this is the third term. Finally, when this charge comes here, this with this with this, and these two with each other. So again three terms, one and two terms over here. That is final. Initially it was at rest. So initial kinetic energy is 0. Final kinetic energy half mv square. That's it. After this, it's purely just substitution of the values. It's just pure substitution of the values. K value, you will put it as K value, you will just put it as 9 into 10 to the power 9. Q value, you will put it as 2 micro. So 2 micro. Q3, 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 Q3 is how much? Q3 is 4 micro. 4 micro, but it is with a negative sign, the whole thing divided by the distance is 5, okay, and multiplied by 2, and this is equal to all these things over here, K is again 9 into 10 to the power 9. Q3 is 2 micro into minus 4, 2 micro into minus 4 micro, whole thing divided by the distance plus half into mass. Mass is how much? 1 gram. So 10 to the power minus 3 into V square. Solving this, you will get the value of V square and then you will get the value of V, which comes out to be as 6.2 meters per second. 6.2 meters per second. This is a very good question. That's why it's level 3. This is level 3 question. Understood? How to solve it? Yes, this is advanced. That's why level 3. It's advanced. That's why level 3. I hope this is clear. Mesu, it will be for more 1 hour. Expect it for more 1 hour. Okay. Now let's come to another interesting thing before we go on to dipoles. Okay. And that is the relationship between the field and the potential. This is another very, very, very important thing. One thing you would have understood, any charge around it creates field. Any charge around it also creates potential. So if a charge is able to create potential and field, why won't they be related to each other? Just like this diagram over here shows some system of charges. You can see some positive and negative charges. You can see these lines. These curved lines are those electric fields going from positive to negative, and those shaded regions is basically the potentials at different points. So the potentials and the fields are actually related to each other. That is what I want you to realize. Whenever you take a, let's say, positive charge, probably should you here, whenever you take a positive charge, you will see that around it, I have regions where the potentials are same, because at the same distance voltages are same. All these points are equipotential. I can go real far also, let's say over here. At all these points, again, the potentials are going to be the same. I go even a little bit more far. Again, at all these points on this big circle, you will see the potentials are going to be the same. These are all concentric circles. And here I can call the potential to be V3. Here it is V2. Here it is V1. All these points, same potential. All these points, same potential. All these points, same potential. So these are called as equipotential lines or surfaces. Equipotential lines or surfaces. On the equipotential lines or surfaces, the potential remains the same. The potentials remains the same. So I can also have the equipotential lines looking probably something like this. I can also have the equipotential lines looking something like this. This is V1, this is V2, this is V3. and so on and so forth. Okay, so I can have equipotential lines looking like this: V1, V2, V3, etc. If by chance I go from this point to this point, understand I'm on the same voltage line, so the voltage difference will be zero. The voltage difference will be zero. But if I happen to jump from this point to this point, doesn't matter which path I take, then definitely there is a voltage difference. The voltage difference will be V3 minus V1, final minus initial. I've gone from here to here, so there is definitely a potential difference. There is definitely a potential difference. I hope that is clear. Not just that, you will also notice that if I happen to superimpose, if I happen to superimpose the electric field lines, meaning this is the electric field line. So many more field lines will be there. Let me show it like this. These are basically your electric field lines. You will notice that these electric field lines, no matter where they are always perpendicular to the equipotential lines. Are you seeing that? No matter where you go, they are perpendicular to the equipotential lines. So, on this same diagram, if I happen to show the electric field lines, I will have to drop it perpendicular to the equipotential lines. I will have to drop it perpendicular to the equipotential lines. Maybe it is little difficult, but maybe it is like this. This is how the electric field lines might look like. Always perpendicular. Always perpendicular. So the electric field lines are always going to be perpendicular, to the equipotential lines. Equipotential lines. This is a very, very important property which you will see. Very, very important property which you will see. Not just that. Thank you, Vedantu Conqueror. Glad you are liking the VBuddy classes. Another important thing about the electric field lines is that notice as we go far away, the potential reduces from this positive charge. Electric field is going from higher voltage to lower voltage to even lower voltage. So here also, if I'm going like this, that means V1 is more, V2 is less, V3 is even less. So always electric field will travel. Electric field lines will always travel from high potential high potential to a lower potential. This is always a fact. All these properties you definitely must know. Okay, all these properties you must definitely know. Is this point clear, everyone? Okay, it makes sense also. If you are at a high voltage, obviously the field will bring you to a lower potential, and there will be a voltage difference created. Okay, if you go along the same potential line, then there is no voltage difference at all. There is no work done at all because potentials are same. Only when you jump the potential lines will you see the voltage difference occurring. This is another important thing. Yeah, clear. Very good. Excellent. Excellent. Now, if I am jumping from one voltage to the other voltage via some random path, just like over here, I'm going like this, taking a charged particle. Understand, there will be also work done to take that charge from here to here. There will be also potential energy which will differ. Just like at this particular point number 1, the energy would have been the potential at that point the potential at that point, which is basically V1, V1 into the charge. Okay, that is the potential at that particular potential energy at that point. How? Because potential is joules per coulomb into the coulombs will give me the joules of energy. Joules per coulomb into the joules will give me the joules of energy there. Similarly, at this particular point number 2, the energy at that point, the energy at that point would have been the potential at that point multiplied by the charge. So think about it. If I subtract U2 with U1, if I subtract U2 minus U1, basically delta U, it is nothing but U2 minus U1. What will I get? What will I get? Think about it. That charge which is there, it will be common. That charge which is there, it will be common. And what I will have is V2 minus V1. What is V2 minus V1? It is the potential difference. This is nothing but the charge. That's it. That is going to give me the energy, potential energy change. That is going to give me how much has my potential energy changed. That potential energy, where will it come from? Who is going to change that energy? Somebody has to do some work. So this will come from some kind of external work. This will come from some kind of external work. Keep this in mind. Very, very important. Also, bear this in mind, back in 11th standard, or you will study it later on, that change in the energy is also technically the negative, is also technically the negative of the work done by electric force. This is way different. Electric force is that internal force, the electric field which is doing the work. External is somebody else pushing it. So this is negative of that. This is something which you have learned long time back in work power energy chapter. Delta U is negative work done by conservative force. So electric force is that conservative force. Now this statement is so important and also so confusing because many students often make mistakes over here. Often make many mistakes over here. So let's try to do a question so that we are, understanding the concept really well. Let's say, for example's sake, a 2 coulomb charge, a 2 coulomb charge is taken as shown, Find the work done by the external force, work done by the electric force, the potential difference, and the potential energy difference. And the paths are as follows. So this is minus 10 volts and this is 30 volts, okay, plus 30 volts. So this is what it is, and you have taken the charge from here via this particular path, okay, to over here. This is how you have taken that, how much? 2 coulomb of charge, 2 coulomb of charge. So let's try to solve this particular question. Come on. First things first, tell me quickly what is the potential difference. That is the easy part. Final minus initial, always final minus initial, V2 minus V1, that is 30 minus 10. So hence the answer should be 40 volts. Just check that out. Voltage difference is 40 volts. Everybody with me? Okay, very good. Next important thing is the work done. Next important thing is the work done and the energy difference. So let's try to find out how much is the energy difference. The energy difference will be charge into the voltage difference as per this formula. Delta U is charge into the voltage difference. So let's try to find it. Charge is 2, voltage difference 40. So it will be basically 80 joules. So the energy difference is 80 joules. Next thing, what is the work done by the external force? It is always a delta U. So hence that external force's work done is also 80 joules. External force has done 80 joules of work. What about the work done by electric force? It is negative delta U. So it has done minus 80 joules. So that also we found. This is how you solve these questions. I hope after this, at least the sign you will not confuse and you know what is what. Okay, everyone, till this point clear? This is one of the most easy but important problem. See, some problems are easy, but you know what? In the exam, you will always, if you don't understand it properly, you'll always get confused. What was negative? What was positive? Who is multiplied by whom? Etc. etc. So I have explained this to you very, very clearly. Also, the properties of electric field lines with respect to equipotential lines. Now, there is a formula which relates both of them, electric field and this thing. It goes something like this. Say, guys, your force, or rather, do it like this. The change in the potential energy is negative work done by the conservative force. So that work done, I can say it is F into displacement, that conservative force, that conservative electric force into the displacement. Therefore, we get the conservative force is minus du by dr. You would have seen this equation even in work power energy chapter. Now, what I will do, I will divide this energy with a charge and this force also with a test charge. If I divide force with the test charge, what do I get? Obviously, force per unit test charge is nothing but field. And what do I get if I divide energy with charge? Just go back over here. If I divide energy with the charge, I will get voltage difference. Energy, Q, if I bring it down, I will get voltage difference. So hence, this should be nothing but dV. And this dr remains as it is. So this is a very, very important relationship. Electric field is negative rate of change of voltage. Is negative rate of change of voltage with distance. As simple as that. Sometimes the dV by dr is also called as a voltage gradient. So it is also called as negative voltage gradient. Voltage gradient. Okay. So field, so electric field, so electric field is negative rate of change of voltage. As simple as that. That is what it is. Yes, Divakar, very good. Kalairal Velusamy, every day 5 o'clock classes on weekdays, Monday to Friday. Okay, you will have classes. Is that okay? Monday to Friday, correct. Moving on to some questions. But before I show you the questions, let me tell you a very simple example. Let's say if I tell you, the voltage is x cube. Can you find me the field? What you will do is you will just say electric field is minus dV by dx because voltage is a function of x. So it will be minus derivative of x cube. X cube's derivative is 3x square. That's it. So electric field is minus 3x square. So if the question demands, can you also find the electric field at x is equal to 2 meters? Then you will just substitute it over here. So electric field will be minus, instead of x, you will put 2 square. So 2. So it will become 2 square, which is 4. 4 3s are 12. So minus 12 volts per meter or Newton per Coulomb, whatever you want to use. So that is the electric field value. Is that okay? That is how we'll solve those kind of questions. Can we differentiate voltage with respect to R to get field? Yes, that is what we have done, Divakar. We have differentiated the voltage with respect to the distance to get the field. Exactly what we have done, but with a negative sign. That's all. Okay, so let's try to solve this. Let's try to solve this particular question over here. Let's say if I put a question like this, electric field, no, not electric field, voltage is, let's say, x square plus y minus 3. Can you find the field? Can you find the field? That is the question. Can you find the field? That is the question. Now there is more x as well as y in the equation, so that becomes a tricky part. That becomes a Tricky part. Yeah. Yes. सर वर्क डन इज इक्वल टू माइनस डी यू, ये वर्क डन एक्सटर्नल एजेंट का है या फिर फील्ड का? ऑलवेज दैट वर्क डन इज ऑफ द फील्ड और द कंजर्वेटिव फोर्स, हु इज दैट? खुशगारा शर्मा. Kushgara Sharma, that is of always the conservative force. So this point, where is it? Yeah. Do you see this work? Conservative. Conservative means who are the conservative things? Who are those conservative things? Conservative is like gravity, spring, electric, like that. Okay. Always this is for conservative forces work done only. So this force, conservative, electric force, spring force, gravitational force. So in this case, we are referring to electric force. So that's why that force divided by the charge will give me the electric field. If it was force by mass, it would give me gravitational field. Okay, that's what it is. Okay, let's try to solve this question. Let's try to solve this question. At the beginning, what to do to solve the problem? Yes, Karthi. So first of all, because you can see it is a relation in x and y both, so we'll separately differentiate x and y, okay, and then find each component separately. See, think about it. If I just have to find x component, I just have to differentiate the voltage with respect to x. If I have to find the y component, obviously I'll just have to differentiate it with respect to y, and everything else is a constant. So now when I differentiate it with respect to y, what is that? X square plus y minus 3. Think about it. X is going to be a constant. Rate of change of y, not x. X is not changing. Only y is changing. So when I move along y will x change. X is a constant. So treat it like a constant, just like that number 3. Treat it like a constant, just like this number negative 3. So it will be 0 plus just the derivative of y with respect to y minus again 0. This is 0. This is also 0. Y's derivative with respect to y is 1. Similarly, over here, when I differentiate it with respect to x, which is x square plus y minus 3, I'm differentiating with respect to x. So x is changing, y is a constant. Just treat it like a constant. So it is just the derivative of x square. This is 0 and this is also 0. So x square's derivative is 2x. So this is x component, this is the y component. So the final answer of the electric field will be x component. Did I miss that minus sign somewhere? Yep, yep. Okay, and did I miss the minus sign here? Yes, definitely. So this was also minus. So this is minus. Okay, perfect. Now it is okay. All right, so electric field will be minus 2x. This is x component, so I cap. The y component is minus 1 j cap, so minus j cap. Newton per Coulomb. That is the answer. Is that clear how to solve this? Is that clear, my dear students? So this particular part 2x, that was your ex component, and this particular part over here, that was your ey component. That is how you solve these questions. Cool, everyone? Yep. Asif, you can do one thing very simple. Just search for over here basic maths. Basic maths. Okay, not this maths, this is that maths. I have done this, do this before studying 12th. Okay, you can study that. Also, where is, yeah, this basic maths. This is basic maths in physics, quadratic and algebra. This particular, lectures are already there. You can use that. But if you still feel that, okay, sir, I'm not able to understand, leave comments. I will see if there are more comments, then I will definitely take it up for all of you. Is that okay? Shall we go ahead? Cool. Okay. Yes, for external agent Kushgara, you can write work done is equal to plus du. In fact, that is what I have written also, Kushgara. Let me just show it to you. That is what I have written also. See, this work done is plus delta u for external. For internal, basically electric force, I have written delta u is minus work done. I have written it already. Whatever you are saying, I have already written it down properly. So, I mean, these notes, now you keep it with you in your notebook, in your short notes, whatever, because I'm making this slides with a lot of efforts, with all the colors, everything, so that it registers in your head properly. Okay, cool. Shall we go ahead? All right, let's go ahead. Let's talk about dipoles now. Let's talk about dipoles. What is this dipoles? Dipoles. Di is basically two. Poles is basically polarities. Polarities. Polarities are positive and negative. Polarities are positive and negative. So when you have two equal but opposite charges, two equal but opposite charges separated by a small distance, separated by a small distance, then that is called as a dipole. Then that is called as a dipole. This dipole also generates something called as a dipole moment, which tells you the effect of that particular dipole which it will have on its surroundings, maybe the field and the potential. So say for example, you take a negative charge and a positive charge like so, and there is some distance between them. Let's say I call it as L. Let's say the positive charge is plus Q, the negative charge is minus Q. Then there is a dipole moment which is formed from negative to the positive side. Be very, very careful. I am repeating again, not from positive to negative, because see, electric field will go from positive to negative. Dipole moment is a vector which has been defined from negative to positive. This is your dipole moment. This is your dipole moment, P. So dipole moment is always separation multiplied by any one of the charge. That's the dipole moment. So magnitude wise, the dipole moment will be either you take this charge or that charge, just the magnitude of it, and multiply it with the length separation, which is L. That's it. That is basically your dipole moment. The unit of this particular dipole moment, separation is in meters, charge is in coulomb, so it is basically coulomb meters. It's not centimeters, cm, it is not centimeters, it is coulomb meters. Now what is the problem is that when you see your NCERT books and all, you will see this number as 2L and then this 2L. I mean, why would you do that? I mean, I understand that later on you might have to bisect it and you measure it all the distances from the center of the dipole. But for that alone reason, writing it as 2L is very, very misleading. Imagine I ask you what is the distance between you and your home and the school, and you say, sir, the distance is 2x. Well, 2x is equal to 500 meters. And then you are like, x is the distance. I'll be like, why are you saying 2x is equal to 500? Where x is the distance between my home and the school. Why can't you just say it is 250 meters? Right? So that is the point. So no need of writing that 2L. I am repeating again, no need of writing 2L. If you are using 2L, then use 2L everywhere and know what the 2L means. 2L is the total distance. L is the midpoint to the distance till the charge. That will create unnecessary confusion for all of you. Yes, correct. In all my lectures, I am saying this. Looks like Divakar. Who is it? Divakar? Oh, Divakar has been following all my lectures. What else should I say differently? Because this is a common mistake and every year people do the same thing. Okay. And what is the direction? The direction, this is a vector quantity, by the way. It's a vector quantity, and that vector quantity's direction is always from negative to positive. Negative to positive. It is negative to positive. Very, very important thing. All right. So this is a dipole moment, which is charge into length. Unit is coulomb meters. And yes, you can see negative to positive charge. Oh, see, here also somebody has written 2A because This is how it is written in NCERT. Okay, so A and A, not needed. You can just write it as L. Who cares about that 2A? All right. So let's go and solve some questions. Do we have a question? Yes. System of two charges, QB and QA. Separation is given by the coordinates. How much charge is given is also there printed. Find the total charge and find the dipole moment. Extremely straightforward problem of level 1. Very good, Tivakar. Thank you. Karthikeyan, if you are facing difficulty in solving problems, just check my, first of all, yesterday's video. I have told some 3-step approach of solving the questions. How many questions you need to solve per chapter. Also, what is the approach of any chapter to be completed. Most important thing, don't focus on too much of note making. Focus on watching the lecture, reading minimal, and maximum time problem solving. In that problem solving, 50% time, believe me, goes in just the basic problems, solved examples, below average questions and all of that. The remaining 50% goes in solving advanced questions, PYQs, and more difficult above average questions. So that first 50% time is the most difficult time. So are able to if you are able to systematically improve your level, right, from the basic to the highest level, and that happens with a proper textbook or basically a proper problem solving book. You start from level 1, level 2, level 3, level 4, then you will get that confidence, and you have to spend a lot of time practicing the same problems again and again, solving at least 2 to 4 questions of the same model, watching a teacher solving those questions again and again. Only then you will get adequate confidence to solve the questions. Thank you, Love Physics, for all the love from Kerala. Thank you. Okay, so my dear students, over here, what is there? The distance of separation. How much is this? This is 15. This is minus 15. So that is 30 centimeters, obviously, which is 0.3 meters. And the dipole moment will be charge 2.5 10 to the power minus 7 into 0.3. 3 you take it here, so it will become 7.5 into 10 to the power minus 8 Coulomb meter. 7.5 into 10 to the power minus 8, how many of you wrote it? Yes, very good. But what is the direction? A is positive, this is positive, B is negative, so always from negative to positive, so it is downwards. So dipole moment vector form will be 7.5 into 10 to the power minus 8 downwards, meaning minus k hat. This is Coulomb meter. This is the correct way of writing it, minus k hat. Do you see this minus? That is exactly this, minus k hat, exactly. And one of the other question was the total charge. Obviously, the total charge is going to be 0 because there is equal amount of positive and negative. There is negative and positive, so the total charge will be 0. Very good. Moving on to the next one. 3 charges are arranged at the vertices of an equilateral triangle as shown in the figure. Find the dipole moment of the combination. Find the dipole moment of the combination. Come on. Now you might be wondering, where is the dipole, sir? Where is it? Well. I'll tell you, you can break this system into 2 dipoles. How? I'll show it to you, don't worry. See, there is one negative charge here, fine. There is another negative charge here, fine. But there is 2 positive charges here. Split it, one for each negative charge. One positive here, one positive here. Now you will notice one interesting thing. That there is one dipole which is formed. Oops, not that great, but yeah. One dipole which is formed like this and one dipole which is formed like this. Both the dipole moments are magnitude wise same. Magnitude wise P2 is equal to P1, obviously, but they are inclined at an angle of 60 degrees with respect to each other. So now you have to find the net dipole moment, meaning their vector sum. So the net dipole moment can be found by root of P1 square plus P2 square plus 2 P1 P2 cos, what is the angle? 60. That's it. P1 P2 both are same. So just take P outside or P1 outside. So what you will have is 1 square plus 1 square plus 2 into 1 into 1 into 1 into 1 into cos 60, which is basically half. 2 cancels. 1 plus 1 is 3. So P1 root 3. But what is P1? P1 is dipole moment of any one. So it is Q into distance. What is the distance? D. So QD root 3. So that is the net dipole moment. That is the net dipole moment QD root 3. How many of you got it? No, not root 2. It is root 3. Root 3. So tomorrow I have unit test in my institute. Physics portion is electrostatics, potential and capacitance. I have already solved some 200 questions in a topic but feeling nervous. Jaya happens because this is the year start and first chapter. And the main problem is when you are starting your year first, when you are starting your year academically, 11th or 12th, you want that the year should start really good. And you feel that if it does not go well, then I might not understand anything in the next few months, or you might feel that I am not that great. Oh, I had practiced so much. Oh, I had put in so much of sincere efforts right from the beginning, and all this has happened at the first test only. So, be prepared for anything. I mean, things might go bad, things might go well. So, if it goes well, don't be very overconfident. That is also bad. And if things don't go uh, as expected, then you need to understand what else has happened, what was the mistake that you did. So it's a part and parcel of your life, and you might have lots of ups and downs in the next few months. Don't worry. But what matters is if you study these topics properly, it will be very easy for you if you do not lose your cool in the end after September, October, to revise all these things and score really well in the full syllabus mock tests. There are many students who do very bad in the class tests, unit tests, but do very well in the final tests. It happens every year. Okay. And if you maintain the consistency, students who do well in all the unit tests, obviously they do much better also in the final test. Okay. But if you are too confident initially, then you might also go down. Don't worry, you will do well. All right, cool. So root 3 QD, that is the answer. Moving on to the next one, electric field and potentials due to the dipoles. So let's see what this is. I have made a beautiful slide. Wow, such a beautiful slide, isn't it? Again, this is going to come as printed slide for all of you soon. But first, let's understand what does this mean. Okay, and which side have I shown? Okay. Okay, so that is positive. All right, so let's use the same sides so that it looks less confusing. Okay, so we have a negative charge, we have positive charge, okay, and some distance between them, and the dipole moment is like this, of course. This is the dipole moment. Let me create a duplicate of this. If I ask you how the electric field lines look like and how the equipotential lines look like, so let's start with it. Electric field lines will look something like this. This is approximately how the electric field lines will look like. Very, very approximately. Like these are your electric field lines. Okay. I'll just put it over here. Electric field lines. Similarly, there will be also equipotential lines. Remember, equipotential lines will be just perpendicular to the electric field lines. So if I just happen to show them, first perpendicular, the most important perpendicular, if I show it, It's something like this. It's over here, exactly, bisecting both of them. You know what is so special about this line? It is equidistant from the negative and the positive charge. So actually it is a 0-volt equipotential line. So actually it is a what? 0-volt. 0-volt equipotential line, because it is equidistant from negative and positive charges. So both of them will have the same effect but of the opposite sign. If you go this side, it is more positive. If you go this side, it is more negative. So if you show other other equipotential lines, probably it will be like this. Then probably even like this. It's got a little bit difficult to draw, but still I'm trying my best. These are the equipotential lines. Looks very scary at first. Looks like some insect or something. Okay, these are your equipotential lines. So do you see that? Are you able to visualize it? Loving the diagram? Understood? Yep. This sides are more positive potentials. Positive potentials because you are closer to the positive charge. Positive potentials. On this side, you will have more negative potentials because you are closer to the negative charge as compared to the positive ones. See, anywhere here, you're closer to this than to this. That's why you are more negative. This is how the electric field and the electric potential lines look like. Now, this is a diagram, fine. But if I want to find value, I can't draw a diagram and expect to get the value, right? So, let me just duplicate this and need it. Now, imagine I want to know the electric field or electric potential at any point. I want to know the electric field and electric potential at any point. So imagine I just from the center, I go anywhere, some random point. It could be here, here, anywhere, some random point. This is at some distance r from the center. At this particular point, if you notice, if you notice, the electric field, you can see it is going like this. So the electric field is in this direction. You can see this is how the electric field is. And at that particular point, you might have some voltage on this particular line. You might have some particular voltage. You might have some particular voltage on that particular line. Do you see that, everyone? Everybody is able to see this clearly? Okay. So how much is that field and how much is that voltage comes via derivation, where you have to find the field due to this, add them vectorially and you get the field. Similarly, potential due to this, add them and you get the total potential. So that derivation, not so important, but main thing is what is the value that you get. So for doing that, let me just extend this line first. The field is making some angle alpha with this yellow dotted line, and this yellow dotted line is making some angle with the dipole moment. Let's say I call it theta. With the dipole moment, the position, how far I am is making some angle, and this is some distance. So this field and this potential is given as follows. This electric field is given by Coulomb's constant, your dipole moment, divided by r cube. R is this. I'll just repeat over here. Here you have your dipole moment, and here you have your r cube, and here inside you have root of 3 cos square theta plus 1. 3 cos square theta plus 1. This is the formula for finding the electric field at some distance r. This is the formula. Kp by r cube root 3 cos square theta plus 1. What an interesting formula. And this angle which the field makes with the position vector can also be written down. So that tan of alpha is actually the tan of theta divided by 2. It is not tan of theta by 2. It is the whole tan thetas by 2. Be very, very careful. So tan alpha is tan theta by 2. That is the other formula which you must know. The last one is of the electric potential. The electric potential at any point is given by Kp. P is that electric dipole moment divided by this time r square, not r cube, r square. That's it. And you put over here cos of theta. You put over here cos theta, cos of theta. That is the value of the potential at that particular point. That is the value of the potential at that particular point. Very, very important. I hope after this you understand what it actually means to find the potential and find the field at any given location. This is the field and the potential diagram. You are actually finding the field and the potential at this point by substituting these values. Now, another important thing over here is there are some special locations in this entire diagram which I will show it to you. I'll just create a duplicate, go down over here, and there are these special locations in this entire thing. One over here is basically this particular position called as the axis of the dipole. This is basically also called as the axis of the dipole. Let me just show it to you over here. This is the axis of the dipole. So anywhere on this line, it is called axial position. This line over here, which is exactly perpendicular to it, that is basically called as the equatorial position. This particular line that you see, this is also called as the equatorial position or equator of that dipole, which is exactly perpendicular. So let me just show it to you over here. This is the equator. This is the equator. Okay. Now, if I use that formulas and find out what is the field on the axis versus field on the equator, etc., the field on the axis, if I use this formula, where is it? Yeah, on the axis, what is the speciality? This point will come here, the theta will become 0. The theta on the axis will definitely become 0 degree. Everybody agrees? So just substitute 0 over here. In fact, it can also become 180 if you are on this side. Then imagine if you are on this side, then the theta value will become 180. That is also okay. So 0 degrees or 180 degrees. Either ways, when you square the cos, because cos of 0 or cos of 180, both is 1 minus 1, squaring it will make it 1. 1 into 3, 3. 3 plus 1, 4. Root of 4 is 2. So hence it will become 2 times Kp divided by the distance, let's say it is r cube. That is what the field on the axis will be. If you go on the equator, then think about it. If you're on the equator, then this angle will become 90 degrees or minus 90. That's okay. So at the equator, the angle theta will become plus or minus 90 degree. So the electric field on the equator will become, just check this out, put cos 90. Cos 90 is 0. 0 into 3, 0. 0 plus 1, 1. Root 1, 1. So Kp by r cube. So it will just become Kp by r cube. That means the field on the axis is basically 2 times the field on the equator. So the field on the axis is 2 times the field on the equator. That's a very interesting relation that you get. Here the field is strong, makes sense, because the lines are closer. Here, if you see the lines are far away, that's why the field is weak. So that number 2 is missing. Here that number 2 has come because lines are closer. So the closeness decides how strong that field is going to be. Hello, Aditya. Is that clear, everyone? If you talk about the voltage, I have already mentioned voltage on the equator will be 0. Voltage on the equator, potential on the equator will always be 0. Okay, it will always be 0. You can see that, right? So this is very, very important. Direct formula based questions come on it. I mean, there is nothing great other than that. Okay, so I think we have done this properly. So Need this. Okay. All these formulas also I kept here. By the way, uh, you don't need this if I have this. Okay. One thing that you should keep in mind, all these formulas, whatever I have written over here, right? These are only applicable under a special condition. That condition, you be careful. That condition is only if you are really, really far away from the dipole. Basically, your dipole length is much smaller as compared to where you are. It cannot be very close by. You have to be really far. Or if you are somewhere, the dipole length is short. The dipole length is short. That means it's a short dipole. So this is the short dipole. So the dipole is basically short as compared to where you are. Only then these formulas are applicable, or else it's going to be just like finding any other normal field or potential. You find the field due to one charge, due to other charge, do the vector addition, find the resultant, just like how you have been doing before. So then it is a standard thing. Okay, these formulas are only applicable for short dipoles, right? So let's see if you guys can solve this particular question coming up on your screen. The distance of the field point on the axis of a small dipole is doubled. By what factor will the field due to the dipole change? Interesting. Think about it and answer. Think about it and answer. Come on, my dear students. What do you think will happen? The distance of the field point on the axis of a small dipole is doubled. By what factor will the electric field due to the dipole change? In general, what is the electric field formula? It is basically Kp root something divided by r cube. So the electric field is inversely proportional to r cube. So think about it. If the distance is doubled, if you make it 2 times, the denominator will become 8 times. So the electric field will become 1/8 of the previous value. Yes, by what factor? 1/8. If it was 8, it will become 1. If it was 16, it will become 2. It will become 8 times of the 1 by 8 times of the previous one. So that is the answer. Is that clear, my dear students? Is that clear, my dear students? Yep. Everyone? All right. All right. One interesting question which I had found for electric field and potential was this one. I think, okay, wait, I'll just put it over here. This was an interesting question which I had seen where there is one dipole here and another dipole here, P and P. Okay, and you are considering a point over here which is having the coordinates a comma 0. The question is find the field over here and also find the potential at this point. It's a very interesting and nice question on the concept of the fields and the potential due to electric dipole. Okay, so basically it is just using these formulas properly. So let's try to see how do we solve this particular question. So first of all, let's go with the potential first because I feel that is the easier part of the two. Then we can go to the field part. Okay. Potential is much easier. Observe this carefully now. Let me split these dipoles into two parts. One dipole horizontal, other dipole vertical. For the horizontal dipole, this point, are you on the axis or are you on the equator? Are you on the axis or are you on the equator? Thank you, JEE preparation, so much. My God, thank you so much for the super chat. You deserve an appreciation. Where is it? Our live class. Let me show this to all of you, even those who are watching it later on. Yes, thank you, Jay Preparation, so much for that humble contribution of 40 bucks. Thank you so much. Means a lot. It shows your immense love and support. So, guys, if students are doing so much for us, you definitely should smash this like button right away, right now. Subscribe to the channel and not just subscribe. Okay, you should also hit all. Okay, so make sure you're subscribed, make sure you are liking this video. Yes, make sure you're doing that. Thank you so much, guys. Thank you so much. Means a lot. These small gestures truly. Okay, Now, because of this blue dipole, you are on the axis. Okay. So at this point, or as you are on the axis, the dipole's contribution in the potential will be Kp cos 0. Remember, because you are on the axis, theta will be 0 degree divided by distance, which is basically a square. Okay, so it will become Kp by a square. Kp by a square. Because of this dipole, you are on the equator, isn't it? For this particular dipole, just think about it. What is this position? It is an equatorial position. So the potential on the equator is always a big fat zero. That is something what I have been telling you here also. Where is it? Potential on the equator is zero. If you are not on the equator, just use this formula which I have been giving you. Where is that? Kp cos theta by r square. Already given. Perfect. So, hence, if I ask you what is the total potential, what is the total potential because of both the dipoles, add this with this, it will just be Kp by a square plus 0, which is just Kp by a square. That's it. That is the answer of the total voltage at that particular point. Yes or no? Everyone with me? Everyone with me? Clear? Excellent day. Now that this is understood, let's go to the more tougher part. Yeah, I'll tell you why it is the tougher part, because a lot of students make some stupid mistakes here, and that is why we should discuss this problem. Imagine for this horizontal dipole, you are again on the axis. This point is on the axis. So on the axis, the electric field is Kp, but 2 times, remember, 2 times Kp by distance cube. Perfect. If you consider this particular dipole, you are on the equator. So the electric field on the equator is just Kp divided by a cube. So like, okay, let me add them. But be very careful. Electric field is a vector. It's not like simple potential where you just add them just with a plus minus sign. No, you can't do that. It's a vector. Potential was a scalar. So that is the catch. That is the catch. Did you get it? So how do you resolve the catch? Okay, I can't just add them directly. I need to see the directions. On the axis, notice, coming back over here. When you are on the axis, the electric field lines are along the dipole moment. Check this out. Electric field is along the dipole moment. When you are on the equator, check this out. The electric fields are opposite to the dipole moment. Yes or no? On the equator, electric field lines are opposite to the dipole moment. Very, very important and interesting thing. You can see that the electric field is basically anti-parallel, over here, whereas over here, the electric field on the axis is parallel to the dipole moment. So that is the thing which you need to keep in mind, which you saw from there. Coming back over here. So for the axial part, the electric field will be like this. Electric field for the axial part. For the equatorial part, it will be anti-parallel. That means it will be opposite to this dipole moment. So this is E equatorial. Now we know where the net field will be. It will be in this direction. This is the net electric field, and since both of them were perpendicular to each other, so this electric field will be electric field along the axis square plus electric field along the equatorial square, Pythagoras. Both are not same, but some terms are common, like Kp by a cube. So I'll have root of 2 square plus 1 square, or 2 square 4, 4 plus 1 5. So it will become Kp root 5 by a cube. That is the net electric field. What an interesting question. What an interesting question. Perfecto. Always. Thank you, Yashwant. Clear? Everybody with me? Right? Amazing, right? So this is a very good problem where that confusion of electric field's direction happens, and when to use which formula happens, and the best part is in the electric field where the electric field is only in a different direction. All right. So this is a proper, I would say, level 3 question. There's a proper level 3 question. So I hope you enjoyed this question. Let's go to the final part where you have dipole in an external field. Where you have dipole in an external field. Okay. So we just now studied that an electric dipole basically creates its own field and potential. But what happens when you put this dipole in somebody else's field? In somebody else's field. That is the last concept in this particular chapter. By the way, let me tell you, I'm following HC Verma flow. I'm following HC Verma flow. So whatever is there in HC Verma, very, very similar, give or take 90%. 90% of the flow I'm maintaining through HC Verma book. Okay. So yes, let's see. Now imagine I have an dipole. This is positive, this is negative, and maybe I have some, okay, I have some electric field going like this, like this. This is some electric field. This is 100% non-uniform, non-uniform. And if you notice, on the negative charge, this electric field will apply a force. Maybe this is F negative. On this, it will apply a force like this, F positive. Why this way? Because on the positive charge, the field and the force are parallel. On the negative charge, the force and the field are opposite. That's why like this. These forces are in weird directions, like you can see. So if I try to find the net force, which is F plus F minus, 100% it is not zero. Not just that, if I try to find the torque on the torque on the dipole, obviously these forces are not collinear. Remember, only when you have collinear forces, the torque is zero. But the moment the forces are like this, or one of the forces like this and the other is like this, then the torque is not zero, right? So these forces are definitely not collinear. You can see that definitely the torque on it is not zero. The torque on it is not zero. So there is some torque which is going to act on it and it will try to rotate it 100%. So if you have a non-uniform field, depending on case to case, there might be force, there might not be force, there might be torque, there might not be torque, but main thing is net force is not zero. Torque being there, not there, that's secondary. But force, well, that is different. That is different direction, different magnitude also. So net force is not zero in a non-uniform field. But the moment I switch over to a uniform field, things change. See, this is uniform field. What is the speciality of this? The speciality of this is uniform field of somebody else. Because the field is uniform, what you will see is that the force on the positive charge versus the force on the negative charge, both are equal and opposite, because the field here is same. Force on positive in the direction, force on negative opposite the direction, equal and opposite. So if one were to calculate the net force on it, the answer will be a big fat zero. So the net force on a dipole on a dipole in uniform field in a uniform field is always zero. This is very, very important. Is always zero. But in a non-uniform field, you can see there are cases where it may not be zero. But here it is always zero in uniform field, and that to the net force. This is very, very important. Now you might be wondering, is there any torque acting on it? The answer is, well, there is torque in this situation because the forces are not along the same line. They are separated by some distance. But if the orientation was slightly different, maybe there would be no torque. So if you talk about the torque may or may not be 0. May or may not be 0 because it depends on the orientation. It depends on orientation of that particular dipole. Let me explain how. Imagine the dipole was like this versus like this versus like this. And the external electric field which is there, it is like this, it is like this, and like this. If you notice over here, the force on the positive is like this, force on the negative is like this. Here, force on the positive is like this, force on the negative is like this. Force on negative is this way, force on positive is this way. In this particular problem, I hope you see that because of these two forces, there is definitely a torque this way. In this problem, forces are collinear, so the torque is a big fat 0. In this problem, these two forces will tilt the dipole in this particular manner, so there is torque in clockwise direction. So clearly, the torque depends on the orientation, so it may or may not be 0. Is this point clear? Is this point absolutely clear, my dear students? Now, if I ask you, how much is the torque? Well, that's not a big task to find. See, this is the dipole. This is the dipole of certain length, and there is plus q charge and minus q charge over here. And you have a force over here, and you also have the force over here. To find the torque, right? The general formula for torque of a couple, this is also like a couple force. This is like a couple force, by the way, because forces are equal and opposite. So for a couple force, the torque that you will find, the torque, the torque that you will find is always any one of the couple force, one of the couple force multiplied by the perpendicular distance between the forces, meaning if I drop a perpendicular distance between the forces, so multiplied by the perpendicular distance between the forces. So multiplied, you get the torque. You will get the torque. That's it. As simple as that. So here the torque will be any one of the force is basically F. In the later on stage, I will write it as Q into E. The perpendicular distance, well, let's say this is theta. So this is L. So this is L sine theta. So this is L sine theta. Now you can see charge and length can be combined together and written down as P. And electric field, let me just keep it as it is. This is your electric field, the one over here. So as it is, and sine theta also I'll leave it as it is. P is sine theta. So that is basically your torque. That is basically your torque. Now the best part is P is a vector, E is a vector. Yes, P is a vector, E is a vector, electric field. Electric field is also a vector. Electric field is in this direction. And theta, sine theta, wow, this is a vector product, 100%. Vector into sine theta, vector product. So guys, I can write this as torque vector is the electrical dipole moment cross the electric field. Cross the electric field. So this is a very, very important relationship of the torque acting on the dipole. P cross E. P is sine theta. Wow, Luxury Hitler, my 2024 batch student. Where are you these days? Counseling process is going to begin. Madhumita Ramesh, I am expecting it to be completed in August, September. That is the target because we are going in full swing. If you notice, like 2 chapters per week, if you just, even think about it per subject, that's around roughly 5 to 6 chapters per week we are trying to complete. So not much time. August, September. September we are targeting. Yeah, we should be done by that. Okay. Yes, same energy, because and for every student coming every year, I am the same, right? I mean, it has to be the same. You can't say that I had a lot of energy in 2020, now in 2023 less energy, 2024 even lower energy. Not possible. So you need to have that same energy. In fact, it is getting better, I feel, with a lot of colorful diagrams. Okay, I use little bit lesser colors initially. Now I'm using even more colors. Looks like a coding, right? Python, C++, your syntaxes. It's looking like that. Okay. Yeah, hopefully you will get into NIT. Don't worry. So this is the torque acting on that dipole. Now, the interesting part about this whole thing is when I show it in different arrangements and the feeling that I will get. See, what do I mean by that? Imagine I keep the dipole. Imagine I keep the dipole exactly opposite. Then I slowly turn it like this. Then I make it like this. Then I will make it like this. Then I will make it like this. Then I will keep it like this. Then I will keep it like this. Then I will keep it like this. Just showing you some orientations of the dipole versus the electric field. Versus the electric field. Okay. Electric field is always here. Electric field is always here. Like this. Okay. So assume green is always the electric field. The pink one is always the dipole moment everywhere. Now, in each case, can you think what is the torque direction, if at all, in every single case? I feel, see, P is here, E is here, P cross E, so the torque will be like this. So the torque will be like this, right? Here, if you notice, P is here, E is here, so the torque will be in this direction. Here, this direction. Here, this direction. Here, oh, 0, they are parallel, so the torque will be 0, no torque at all. Here it will be like this. Here again it will be 0 because they are anti-parallel. Sine 180 is 0. Here it will be like this. Here also it will be like this. Looking at all these diagrams, you know what sense I am getting? What sense I am getting? Look at two special positions in this entire diagram. There are two very unique things in this entire diagram. One is this one is this one, and the other one is over here. The other one is over here. Just imagine the dipole was perfectly aligned with the field, perfectly. If I move it slightly on the top, the torque pulls it back. If I move it slightly below, the torque pulls it back. In fact, if I make it perpendicular, like the one here, it still pulls it back over here. If I make it perpendicular down, it pulls it back. If I move it too much behind, still it tries to come back. If I move it the other way, too much back, it again tries to bring it back here. So it's always trying to come back over here. So is it not a position of stable equilibrium? I mean, obviously it is in equilibrium because torque is 0, but it is not any ordinary equilibrium. You try to disturb it, it comes back. You disturb it, it comes back. Some people are there like that. They are so focused on JEE. And I observed this even when I interviewed the toppers. So many of them, it is very simple to talk to them. It's so straightforward with them that I asked them, were there any distractions? No. I asked them, did your friends try to distract you? Well, not so much, but few friends tried to tell me to watch this, watch that. I said, no, I have to watch lectures. Would you like to play outside for this thing? Let's go party. No, I have to study. Uh, School, well, not so important. Boards is not so important. I have to prepare for JEE. It's so straightforward. Like so stable. You try to deviate them, they'll come back. You try to push them here, they'll try to come back. So it's very simple, guys, to become a 99.9 percentile student or to top in JEE. So this is exactly that kind of a thing. So hence, I would say this is a stable equilibrium position. Stable equilibrium position. Do you agree with me? Whereas, just look at this. This is that Low percentile. I mean, in equilibrium, lecture is going on. Equilibrium, lecture is going on. You move it slightly here, zoom, goes to the other side. You move it slightly down, like the one shown here, slightly down, zoom, it goes to the other side. So the dipole over there in that opposite orientation was in equilibrium, but a small disturbance here or here, zoop, it takes it far away from that. So it is highly unstable. It's highly unstable. So this is unstable equilibrium. Do you guys agree with me on this? Do you understand the difference between the two? Yep. Yep. Very good. Very good. Yes, just like me, very focused came to the JEE lecture even after the JEE exam happens. You get so engrossed in the exam, and then finally you will somehow achieve a lot of concentration even after the exam. Crazy it is. Okay, so this was 0 degree angle, this was 180-degree angle. Till this point, I hope everything is clear. By the way, if I ask you when is the torque maximum, well, it is at 90 degree, and you can see it very well, over here. You can see that this is the scenario of torque, max torque, which is at 90 degree plus or minus. This is also maximum torque. This is also maximum torque. Again, this is happening at perpendicular. Okay. So torque is maximum at 90 degree. Great. So you have seen how the torque changes, how the equilibrium positions are, how forces are zero, and how the force may not be zero if it is a non-uniform field. There is one last thing over here. And that last thing is basically the energy. How many of you feel that looking at this diagram, it feels like a spring? It feels like a spring, which is like, it's stable here in this position. If you try to move it here, it comes back. You try to move it here, it comes back. You try to move it here, it again tries to come back. You try to move it here, it again tries to come back. So it's like your spring is being storing some energy and it's bringing it back over here. It feels like that. So this is going to have some kind of electrical potential energy, and we define that energy to be zero when the dipole is perpendicular to the electric field. It's just a convention, don't ask why, but it is a convention that the dipole, when perpendicular, that particular scenario of 90 degrees is taken as zero reference potential. This is your zero reference potential energy, zero reference potential energy. So there is electrical potential energy involved as well over here, and you will see that you can find that again using integration. It's not that difficult. But the main thing is the formula over here. The electrical potential energy comes out to be minus P and into E, minus P into E, and then if let's say for example this is your dipole and this is your electric field and the angle between them is theta, so what comes out is minus PE cos theta. P is a vector, E is a vector, energy is a scalar, and there is cosine. Obviously there must be a dot product over here. So the actual formula turns out to be U is equal to negative P vector dot producted with electric field vector. So this is what the electrical potential energy formula looks like. This is what the electrical potential energy formula looks like. Very, very important. All right. Okay. I hope this is absolutely clear. Awesomeness. Awesomeness. Great. Okay. Cool. So with this, if I go back over here and if I ask you what is the electrical potential energy in this situation of unstable equilibrium, the answer will be, check this out, minus P E cos 180, because theta will be 180, Cos 180 is minus 1. Minus 1 into minus 1 plus 1. So it will become plus PE. So it will become plus PE. If you ask me what is the potential energy here in this scenario, so you will be like, okay, let me just figure it out. Theta is 0 degree. Substitute 0. Cos 0 is 1. So it will become minus PE. So it will just become minus PE. Interesting thing is, this is the minimum potential energy which you can have, and this is the maximum potential energy which you can have. And it kind of makes sense because when you are unstable, your energy will be very high. Unstable, too much energy, hyper, like madness, you have energy. So maximum energy at unstable and least energy, in fact, negative energy in the stable equilibrium position. That is what it is. Very nice. Cool. So maybe we can solve a question on this. What do we have? Positive charge is fixed at the origin of the coordinates, and electric dipole, which is free to move and rotate, is placed on the positive x-axis. Its moment is directed away from the origin. The dipole will, what will it do? Draw the diagram. It's a non-uniform field question. It's a non-uniform field question. Think about it. It's a non-uniform electric field question. How? Because look at it. A positive charge is fixed at the origin. So you have a positive charge which is fixed at the origin. This is your x-axis, this is your y-axis. An electric dipole which is free to move and rotate is placed on the positive x-axis. Free to move such that the moment is directed away from the origin. So this is how you have placed the electric dipole moment. Now, interesting thing to note is how the electric field lines will come out of this. How the electric field lines will come out of this. Electric field lines will be like this, then like this, like this. Notice this is how the electric field lines will come out of this. 100% these electric field lines are non-uniform. In fact, the field is very strong here and it is very, very weak as you go far away. So which means when you calculate the force on the negative charge, the force will be higher, versus on the positive charge, the force will be smaller. These both won't be equal. F negative magnitude wise will be more than F positive. So hence the net force on it, will be there towards the, origin. So what will it do? It will move towards the origin. That is the answer. It will be the answer. There will be no torque on it because both the forces are collinear. The net torque will be 0 since the forces are collinear. Forces are collinear forces. So they cannot produce any torque. Only when you do this, there is a torque. When the forces are along the same line, how will there be a torque? There must be some separation. Okay, there must be some separation. So that separation is absent. So hence there is no torque, but there is net force towards the origin. Is that interesting, everyone? Clear? Okay. All right. Perfect. Moving on to the next question. What do we have? Two charges, level 2 question, of magnitude are separated by 0.4 millimeters, makes a dipole. The dipole is placed in a uniform field of 10 dyne per coulomb, making 30 degree with E. The magnitude of the torque is how much? Field is given in dynes per coulomb, angle is given, distance is given, charge is given. Finding the torque. Well. Torque is PE sine theta. Dipole moment is charge into length. So charge into length into field into sine of 30 degree. So I think now you just have to substitute every single value. The charge is 0.01. So instead of Q, you will put 0.01. Length 0.4 millimeters. So 0.4 into 10 to the power minus 3 into the field 10 dynes. Well, 1 Newton is 10 to the power 5 dynes. 1 dyne is 10 to the power minus 5 newtons. So 10 into 10 to the power minus 5 newtons, and Coulomb as it is. Sine 30 is just half. Come on. 4 is there, 2 is there. So answer will be 2 into something. So check the answer. It is D. I didn't even calculate. I didn't even calculate this. I mean, I just saw only one number is there here and here. So I know the answer will be 2 into 10 to the power something. And that something doesn't matter for me because there is only one option with the number 2. So directly I will mark it as option number D. But I know if I calculate this, I will get it as 10 to the power minus 10. This is called as the ignoring powers of 10, zeros and decimal places. If you have been staying with me for a long time, you already know this trick and technique which we have been using for calculation purposes, right? Very simple, because the decimal places don't matter, the powers of 10 don't matter, the zeros don't matter. Numerical value will be 4 by 2. 4 by 2, which is 2, is only there in one option. If 2 was there in two options or three options, then there was no other choice but to solve the complete powers of 10. That is the trick for it. Okay. Well, that is the lecture. We have completed this chapter. Part 1. Part 2, basically Gauss's law, is a separate chapter in H.C. Verma and many books. Obviously, if you are using coaching material also, many times it is separately printed. So we'll be doing it on Tuesday, if I'm not wrong, or worst case Friday. And till then, please revise this chapter properly, solve the questions, solve the DPPs. The Jungle book will contain the DPP of every single chapter. Check it out. The link of the Jungle book is there in the description box. Basically, Jungle book is a single resource sheet for all the subjects, all the lectures, no playlist required anymore. You will get all the lectures arranged in the sheet. The notes will be arranged in the sheet. The DPPs will be arranged in the sheet. So everything in one single place, my dear students. Okay, so that's why we call it as the Jungle book. And our series is Lion. Come on, Roar series. So that's why we have the Jungle theme. So if you loved this lecture, I want every single student of 12th standard put up in the comments 12th standard started. Everybody in the comments 12th 12th started. 12th started with full Josh or with a heart, with a smiley, whatever you want to put. But everybody is going to comment this. Okay. Thank you so much, guys. Thank you. And if you have not had dinner, please have it. Okay. We'll be meeting very soon. Bye bye. Captain Shreyas signing off. Hasta la vista.